All right, we are now recording, and we'll pick up at this slide, but before we get there, anybody can turn on projector. Okay. Let me go over just a couple of things. I don't think any are all that urgent, but I forgot to bring it in, but I believe the Birmingham Sidewalk Film Festival is this weekend, Friday, Saturday, Sunday. I think some Lawson State students are participating in various ways in it, and I think at least one instructor, Ms. Morgan, is participating in it in some ways. So that's happening. All right. I think we went through all the stuff before, but let me just bring you a little bit of an update. I don't have much to update. Of course, I thought I would have 2 hours of office hours yesterday. Technically, I did, but I spent most of them with dealing with administrative stuff. I got very little done on course stuff. I have no office hours today to speak of, and tomorrow I'll be on the Birmingham campus, and I'm hoping to get caught up on a lot of the things, like your syllabus updated and the various things done. And let's see, should be able to find you, but so far I can't. Chelsea, right?
Yes.
Okay. Okay. Anyone else come in since I called roll? Okay. So I can't swear to you that I will be have everything caught up in Blackboard tomorrow, because I know we'll be canceling classes like crazy, and that means calling students before I cancel and all that kind of stuff. So if I don't get to it tomorrow, hopefully I'll get to it over the weekend. So I can't say for sure, but I'm hoping I'll be able to get that caught up over the weekend. If not, hopefully the 2 hours in office hours I have Monday afternoon, I may be able to finish up then. Can't say for sure. I'm almost certain of this. I probably won't be able to get all your PowerPoints loaded yet, because that means I have to remember to take them over to the Birmingham campus and take them home with me over the weekend. And the likelihood of that happening is pretty slim. They'll just fly right off the coop. But if I can remember to do it, I may get those done too. Okay, now, and another sort of reminder, the first class is out there on in YouTube. I just don't have it set up. I have it in the playlist, but I don't have the link to the class yet. If you know how to look through things in YouTube and can find it, you can watch it. You don't have to have the link, but the link just makes it easier to access. So do that if you can. All right, and let's just wrap up. We made, I think, probably more than halfway through chapter 14 last time. So I'm thinking we're going to finish chapter 14, and yeah, almost certainly we'll finish chapter 14 today. With time, yes.
What type of title does it have on YouTube?
It will say something like PHS111 Syllabus. Now.
Your name and
yeah, and I'll be the one who created it, See, I've never looked up myself on YouTube, so I don't know what it looks like. I just go to my channel, and it's all there, but I don't know how to do it as an outsider. Okay, so because when I log in, it takes me right where I need to go. But yeah, it's now, I've taught this class several times, and from what I understand, once it's on YouTube, it's almost always on YouTube. So you may see several PHS111 syllabi with my name on it. Can you, when you're looking at YouTube, see the most recent one? It does have date and stuff on it. Mine, when I'm into my channel, it never indicates a date to me. But if you can see that, get the one for this time. But it's not going to be much different from the other times either. But but you can follow that. And so what I was saying before, I will finish this chapter 14 and probably get a pretty decent start in 15. But then when 3:45 rolls around, stop me. If I'm not stopped by then, stop me. And we're going to stop, and then I'll pass out the first lab. We're going to do the first lab all as one group. All of you will be participating, or as many as we can get to participate. And we'll get the lab done. And that will be it for today then. Whatever we get from till 3:45 in lecture, and then from 3:45 to 5:45, or if we finish sooner, that'll be lab. Yeah.
They all came up on YouTube.
They did. A whole bunch of them. Physical Science 111 syllabus.
Mm-hmm.
Okay, can you tell which is the most recent?
See one from a day ago.
Yeah, okay, that's it then. Okay. Oh yeah, mine does say that. It says how many days ago. I thought that was just on my side.
1 day, 1 week, 1 year ago.
Yeah, exactly. Okay, yeah. It's the one that says 1 day ago. Okay. So if anyone doesn't know how to do it, she does. Okay. Yeah.
I have a question about, I didn't copy all of the notes that were from the other day.
Right.
Were they straight from the book? Because I know when I quiz next week, we can only use written notes.
Yeah. Pretty much. I mean, I teach from the PowerPoint and from the book. And so it's usually from one of those two. Let's see if I can find Ashley. There she is. Okay. Is that what you were asking? But the other thing is, you can go and watch it all again on.
Oh, that's right. Okay.
Yeah, and you'll see and hear everything. You can't see me point to things, but everything else is there.
Right.
And you can slow it down, I guess, or stop it, or do whatever it takes to get all the notes that way. Yeah, and part of maybe what you're asking there is everything on the slides from the book. Sometimes I have trouble figuring out where they do, but I try to pick out the test questions that I thought were covered best by the slides in the book. I may not always succeed completely, but I tried to do that because the test bank is by the same outfit and everything, but sometimes I'll look at some of those questions and go, where did that come from? So I try to eliminate those if I can. Okay. And so let's go back to that. Someone's already made mention of it. The test for Chapter 14 will be Tuesday, okay? And I'll just give you what I think is a likely scenario for Tuesday. Since we'll finish 14 today and get started in 15, and then have the lab that sort of goes along with 14 today, then Tuesday I'm almost certain we'll finish Chapter 15, and then probably do the lab for 15. But that won't be at 3:45, that'll be at 3:15. That's where I'll stop then, because I want to give you at least a half hour to do the test. I think most of you will be able to finish well before that, because I think the first test is all multiple choice. But like you said in your question, you can have a formula and equation sheet. Anything you want to, not formulas and equations, but just anything you want to write down on a piece of paper to bring with you. And yeah, it's mostly from the text and or from the slideshow. Yeah. What's that?
Chapter 14.
Chapter 14 test will be Tuesday. Yes. Okay. The lab for Chapter 14 will be today. Hopefully we'll get started in 15 today and hopefully finish enough of it by Tuesday. We can do the lab at 3:15 to 5:15 on Tuesday, and even if we don't finish the lab, we'll time out on the lab and give you a full half hour to do the test. So, good deal. Any questions then? Can you see well enough from there? If you want to scoot the table over there, feel free to move around. Because my Monday, Wednesday, 8 o'clock class, we filled every desk. 2 people sat at the table, and I had to bring a desk from next door. I don't know how many we had in here, but it was a lot. So that's why things are like that here. And so feel free to move around whatever you need to be able to see. We may move that other class just because they had one of them, the one who sat nearest the wall, had trouble seeing. So I'm going to see about moving that. All right. Any other questions before we get started today? What we covered in class so far, how we're going to organize the class, whatever. Okay. That's right. Oh, absolutely. Yeah. Anytime, if you need to get up and go, you can. This is. Okay. Now, I think we got to this slide, but I don't think we finished it, did we? In fact, let me, in the text, we're on page 362. It's the beginning of the end for less massive stars, okay? And actually, part of this is probably even the previous topic, red giant stage. I think that's probably where we'll begin here. Let me back up one slide. Second? Yeah. This may be a better place to do stellar evolution. Basically, this would start at the life of a star on page 362. Okay? So this might be better, just to be a little bit of review. Let me see if there's anything before this. Nope, there's life of a star. Let me start there. Life of a star.
This is slide for the stellar evolution.
What's that?
Never mind.
These were the two slides before the one that I was going to start on. I didn't, we sort of ran out of time. Wasn't able to finish the topic. So let's go back to the beginning of that topic. Let me just do one more just to make sure that, okay. I'll put this up. This is the Hertzsprung-Russell diagram. These are main sequence stars. These are giants. What that means generally, red giants. Supergiants, and these are the white dwarfs. Most stars in the middle part, the main part of their life, are in what they call the main sequence. When they begin the end, okay, they become red giants unless they're really, really big stars, and then they become supergiants. And then when they finish through that, some of them will then become white dwarfs. That's what we'll be getting at later.
So that's like the lifespan of a star, how it starts?
Yeah.
It starts off main sequence and then goes to
Actually
giants.
starts before the main sequence, but when it first becomes a star, it enters the main sequence,
So it goes
right?
protostar to main sequence.
The protostar is right before it becomes a star,
Okay.
right? Yeah. Okay, and then when it becomes a star, it's a main sequence star. And it usually lives there for small stars, trillions of years, medium-sized stars, billions of years, large stars, millions of years. So just a little bit of time, okay. And then these things, they don't really give us a good timeline on these, but these go a bit faster than that,
So when we see a shooting star, is that the ones that's in the
All right, okay, good question. A shooting star is not a star at all. We'll cover this in next chapter. A shooting star is a piece of debris that's floating around in our solar system, and when we go through our revolution around the sun, we run into it, and it's a rock, a piece of a comet or something like that, and when it enters our atmosphere, the friction is so great it burns up. So it's not a star at all. That's just the remnants of something else that we ran into. And let's see if I can find your name. Fred? Second? Sam. Okay, I found you. There you are. All right, good deal. Okay, good question though. Any other questions? So, with that in mind, let's look at the life of a star. Now, way back before even it was a cloud of gases. Now, a cloud of gas is not necessarily going to become a star. But all stars come from clouds of gases, okay? So if you had that cloud of gas and everything happened right with it, okay, and it, it had that disturbance that forced the molecules together, you started having gravitational collapse, and they started drawing in more and more of those gases that were in the cloud and pulling them in and pulling them in. That's called gravitational collapse because it gets smaller, it heats up, it gets denser, hotter, and greater pressure. All happening. And if it reaches this 10 million K, whoa, really hot in the center, then fusion begins. Okay, they call it ignition. That's not like striking the match. It's just gets hot enough for fusion to happen. And the hydrogen starts fusing into helium. Once that begins, now you're in the protostar stage. You're at the point where you're going to be a star. You're going to be a star. No, okay. Now, everything has been collapsing so far, drawing in more and more matter. Kind of like a mini black hole. You're just drawing in the matter. These gases are collecting within this area and getting hotter and hotter and hotter. If it reaches that 10 million K, fusion begins. At this point, it's blowing up because fusion gives off a lot of energy. Well, now this is what they call the dynamical equilibrium. The gravity is still trying to pull it in, collapsing it, but the fusion is trying to push it out. Okay? And that's why it's a protostar. It's not steady yet. It's, going through this kind of thing. It's kind of like, y'all probably never driven a car like this. The shocks are going bad on it. You hit a bump, and you do this for a while before you finally settle out again. No, you would never have been there. Okay? That's sort of like that dynamical equilibrium. It's kind of getting the inward force due to gravity, outward pressure by the fusion energy. It reaches some sort of equilibrium. Now the star enters the main sequence. It becomes a star. Okay? And it starts dancing. No, that's a different issue. Okay. And I want to give you plenty of time to get down whatever you need, but also not saying you shouldn't write it. And I think writing down is a great thing to do, but some people actually like to, you don't have those yet. Sorry. As soon as I get the PowerPoints out there, if you want to copy those, then it might save a little bit of writing. However, writing sort of ingrains it a little deeper into the psyche, I think. Okay. This is a picture of that happening, kinda. Gravitational collapse was occurring until the heat got up high enough. Fusion started happening and now started blowing out. So the inward force due to gravity, the outer force due to the fusion energy, when these reach that equilibrium and it stops, sort of settles out, then you become a star. Now, going back to your question, just picture when our sun was starting, about 5 billion years ago or so, whenever that was, and that fusion began happening. It probably blew some stuff. Someone in here, it may have been Hunter, was asking about solar flares. Was it him or somebody else? Yeah, okay. Asking about solar flares. Those kind of things are happening all the time. Back when it was a protostar, I bet you there was a lot of that going on. And when that was going on, stuff started getting spewed out into space. Okay? Now some of that stuff that was spewed later became planets, moons, asteroids, comets, all sorts of stuff, and others just remain junk. Okay? And that junk, when we run into it, it's few and far between, but it's there. That thing gives us some of those meteor, falling shooting stars. Okay? So, now, as we said, it became a star, enters the main sequence, the purple snake, remember? Okay. And it stays there basically, practically its whole life. Okay? But toward the end, then it enters what they call the red giant stage. Okay, now what's happened? You've had gravitational collapse, fusion pushing out. Dynamical equilibrium. Okay? It stayed as main sequence star all that time. But in time, remember a few slides earlier, told you how many SUVs were being lost as that fusion occurs every year, wasn't it? Okay. Quite a bit of mass being lost, quite a bit of hydrogen being fused into helium. At some point, you use it up. There's no hydrogen left. The hydrogen in the core, now it may be out here somewhere, but in the core, that's where the fusion is happening. It's not got enough left. So the hydrogen is exhausted. So what happens? The core collapsed. Because remember, gravity was trying to pull it in, the fusion energy was pushing out, it collapsed. When it collapses, it heats up even more than it was before, which is hard to believe. And as it heats up, the outer shell starts expanding because of that heat. And then as it expands, it cools. So it may have been a yellow star, it may have been a blue star, it may have been something else. But now when it's cooling like that, it becomes a red star. Remember, red is the coolest color, okay? But it's a huge red star, and that's why we call it a red giant. Okay? Now, and as we said before, those hottest stars, the most massive stars, with the most fusion going on, they only live a few millions of years. 10 millions, 100 millions, something like that. The Earth's G, it hangs around about billions of years. We think around 10 billion for the lifetime of the sun. We're about midway through that now. The M stars, which are the very coolest of the stars, now they may be red to begin with, or reddish. They hang around for trillions of years because they just don't burn their fuel. They don't fuse their hydrogen as rapidly. Okay? But the mass determines that ultimate fate. And that's what we're moving to next. Let's just show this. So this is main sequence to red giant, and then you might have a couple of phases in there, and if it collapses, and we'll get to the next part in just a minute, and then ultimately head down to become a white dwarf. This is sort of your average star. Okay? So let's see some of those intermediate phases there. And this is where we're going. Same diagram we just had. So here's the late red giant stage. We're somewhere around in here now. The core began collapsing when you ran out of hydrogen, gravitational. Heats up, which blows out the outer shell because of the heat. But the outer shell gets further away as it cools. That becomes red. Okay, but further core collapse and heating, after a while, I don't know what temperature this is, way beyond, what was the other one, 1 million K or 10 million K or something like that. Now you get hot enough for helium to fuse. You have plenty of helium, that's what you got from fusing hydrogen. Now the helium fuses, and that becomes carbon. Okay? All right. Let's see. Is it Fred?
Yes, sir.
Okay. Great attendance again today. Everybody that was here, -1. Okay.
So hydrogen is what fuses to make the star?
Hydrogen fuses to become helium, and then when the hydrogen's used up and it collapses again and heats up again, even hotter, then the helium fuses to become carbon. And you can sort of picture that on your periodic table. Hydrogen fuses to become helium. When helium fuses, it becomes carbon. Because there's 8 particles in the, 4 particles in the nucleus of helium, And when you fuse those together, like 3 of them fuse together and become carbon, which is 12. So it's high temperatures for that to happen. So when helium fusion happens, now the radius increases because now you got all this blowing out again. You have the nuclear fusion energy. And the luminosity decreases. Okay, I'm sorry, I said that backwards. And this is part that's a little, I find shaky the way they say it here. The radius and the luminosity decrease, and the reason for that is because kind of picture it this way. Back when you were a protostar and the hydrogen first started fusing and started blowing out, okay, your radius was going to increase. But then when it settled down, it started decreasing again. Well, the same thing happened here when you had the gravitational collapse and heating blowing out the outer part, but now when it gets back into a dynamical equilibrium, the radius and the luminosity decrease again and actually comes back into the main sequence. Now it's a helium star rather than a hydrogen star, okay? Now, after a while though, you use up the helium because like I just said, 2 hydrogens make 1 helium. It takes 3 heliums to make a carbon. So you have half as many heliums as you did hydrogen to begin with, but now you use them up 3 times as fast. Okay, so 6 times. Okay, so the helium fuel in the core is used up. The helium and hydrogen fusion in the shells are exhausted. You can't do any more. So what happens now? Its core is again collapsing on itself, blowing off the outer layers when the heat heats up, and that's what leads to that planetary nebula that we saw at the beginning. This is what's left over in the core, and this is what all those gases, remember, in the radiation zone and the convection zone, all those gases are just being blown out into space. Okay? Now, that little core that's left over is still awfully hot. That's why it's white. Okay? The instability blow off the outer layers, forming this planetary nebula. The carbon core contracts again to become a white dwarf. Okay? Now, there's no more fusion. It's so hot from the collapse, but it's not hot enough to fuse anymore. Okay? So over time, it cools off, and it's no longer a white dwarf. It's just a black lump of carbon. Pretty good sized black lump of carbon. Okay? Now, I did not know this, and this is really all speculation, but I had a adjunct physics instructor here who was from the Soviet Union. He was actually natively, how would you say it, genetically, or, he was Russian, but I don't know if y'all have studied much on the history of the Soviet Union. Russia was the biggest of the Soviet states. All the others were little satellites around them. And what Russia did when they took over these other ones, they tried to ship as many of their people out into these others so the others would not be ethnically different from them, or so much so. So he or his family or something got moved to Ukraine, which was all part of the Soviet Union. And it's right next door to Russia, the next biggest state. Been in the news lately too, if you remember. Russia's basically almost trying to pull it back in. And if they have a government that doesn't support Russia, Russia tries to overdo that. Yeah, it's been a mess. Remember Crimea, all that. All that is involved with this. Now, but Dr. Bolshinsky, he or his family or somebody had been moved to Ukraine. But Dr. Bolshinsky worked with the Soviet Space Agency, equivalent to our NASA. The Soviet Union had space agency. Well, when the Soviet Union collapsed, and all those states, other Soviet states, became countries again, like Ukraine, Kazakhstan, Azerbaijan, Georgia. All these became countries again, not part of the USSR. Well, Russia kept a space agency, but these smaller states couldn't. Well, these native Russians that had been sent out to populate the other states were not allowed back into Russia because, no, you're Ukraine. No, we're Russia. No, you're Ukraine. So he was stuck in Ukraine without a space agency because it was back in Russia. So he immigrated to the U.S., hoping to find some work here because there wasn't a lot for him to do in Ukraine. Nice guy, too. Really nice guy. Funny guy in a physics kind of way. And he told me about, and this, supposedly this really happened. Yeah, it did. The first time they found one of these white dwarfs and figured out why they became a white dwarf, okay, that's helium fusing to carbon and then couldn't do any more fusion, okay, and then it collapsed on itself. What happens to carbon when you put it through very high temperatures under high amount of pressure? Say again? It becomes a diamond. So, this shows how weird physicists and astronomers are. The first one of these they discovered and knew and figured out it was a white dwarf. Do you know what they named it? Lucy. Why would they name it Lucy?
What's the song? Right.
Oh, they were Beatles fans. That was it. Lucy in the sky with diamonds. They literally, I'm not making this up, they named that first white dwarf Lucy because they figured it must be, at least contain some diamond out there, and it was out in the sky. Astronomers. That's astronomical humor, by the way. Okay. So that carbon core collapsed, and when they say a black lump of carbon, that doesn't mean its color is black. It means it's not emitting light anymore. The white dwarf is still hot enough to emit light, but over time it cools enough it doesn't emit light. So whether it's carbon, soot, coal, or diamond, it's not emitting light. That's what makes it black. It doesn't mean it's a black chunk of coal. It may be, but the odds are there's probably some diamond in there. And guess what, folks? That's probably where the diamonds we found in our planet, you know, South Africa has a lot of them. Africa in general, major source of diamonds. That probably came from some chunk of the previous star whose gases became our sun ultimately, but got blown out, and that's probably became the part of the Earth. So who knows? Maybe some of the other planets have diamonds in them too. I don't know. Especially the terrestrial ones. Okay, we'll talk about that later. Okay. Say again? I can't hear, sorry. Oh, yeah. The science fiction writer? Yeah. Has he written about that?
I think it was in that book, Cherry.
Yeah, and they go out trying to mine diamonds from, yeah, a pretty expensive process to get a little return, but yeah, very good. Okay. All right. Now, those were the smaller stars. How about the end of the more massive stars? That's probably where our sun's going to go. You know, we're a medium-sized star. We're going to go back to being a black lump of coal or carbon. Yeah. But the more massive stars, they hang around a little bit more. The more mass, the more gravitational concentration you have, the more heating you've got. Now, remember before was it 10 million? 10 million. Now they get up to 600 million K. Goodness gracious. Now carbon fuses. And when carbon fuses, the heavier nuclei, not just carbon, they more and more fuse, and the can fuse up to iron. Later, next chapter or 2 chapters, I can't remember which, we'll find out that the most predominant element in the earth is iron. And there's a reason for that. More than likely, our solar system was formed after some supernova of some huge solar system, or SAR, had collapsed and had a lot of iron left over. And that's why we have a bunch of iron in our core, and most of the other terrestrial planets too. So they will actually fuse up to iron. But at some point, especially when they get as far as iron, all the fusion energy sources are used up. You can't fuse naturally anymore to iron. I mean, just the regular thing. If you go back a chapter or 2 on the nuclear energy section that we're not covering in this book, in this course, you'll see them, read them talk about it. And that's why the book put astronomy after physics, but Alabama does it the other way. Okay, so all the fusion energy is used up, the energy expansion pressure is lost, and the dynamical equilibrium is disrupted. And what happens? You have collapse. But now there's nothing else to fuse, and it gets so stinking hot as it does. Now you blow up into really a supernova. The star collapses and then rebounds from that collapse from the core, and elements now that is such a huge rebound that forces some other fusion to happen, and that's where you get elements beyond iron. See, iron really isn't too far down the periodic table. There it is right there. Fe is number 26. Periodic table goes to 103 or further. No, 118 or further. So iron is just, basically a quarter to a fifth of the way there. But the heavier elements did when that iron, which is as far as you can go in the normal fusion, when you have that supernova and they collapse and then rebound, there's so much force there that you can create elements beyond iron in that explosion, and then they're distributed throughout the universe. Not at very high concentrations. That's why we don't have a lot of uranium, okay, or plutonium, or even platinum, or gold, or silver. Those are all way heavier than iron. These are formed in small amounts, okay, but they're distributed throughout the universe. Okay, that's from the supernova. When our sun dies and collapses, chunk of coal. Okay, that's about all. It may have some other things left over from whatever preceded it, but that's about it. When these super massive stars die, they create all sorts of stuff and then spread them out, and they recollect, and other planets will wind up with some of them. Okay, the subsequent events, again, depends on the mass of the remaining core. Now we're just down to the core. You've blown off everything around it. You're just talking about the core. Okay? Now these are the more massive stars. What happens next? Depends on how big the core is. Everybody ready? All right. Here are the 2 possibilities. For your massive stars, but not the most massive ones. The remaining core now, not all the stuff outside the core, that's been blown away. The remaining core is between 1.4, about 1.5 to 3 times our sun. I mean our entire sun, not just our sun's core, our entire sun. These are much bigger stars. If you're between, that remaining core is between 1.4 and 3 solar masses, the gravitational pressure is so great that it fuses protons and electrons together. Anyone remember what protons and electrons are? Protons are the little positively charged particles that make up that are in the nucleus. And electrons are little negatively charged particles that fly around the nucleus. Say again?
Does it create a magnetic field? Or?
They could, and we'll talk about that in just a second. But you got protons and electrons. Now, most atoms also contain a few neutrons. Neutrons are neutral. They don't have any charge. Okay? Where do those neutrons come from anyway? Well, we won't get there, but here's where some come from. If that gravitational pressure is so great that electrons are fused into the protons, and now there aren't any protons or electrons left, or not many, they're all neutrons. Okay? And that then becomes what we call a neutron star. Now, you talk about one massive bit of material. A neutron has no electrostatic repulsion, or attraction, that they can pack this as tightly as they can. So these are really dense stars. Okay? Now, as you're reading here, a pulsar basically is a pulsing star. That's where that name comes from. It's a short name. A pulsing star. This is rotating, magnetized neutron star. Now, I don't quite understand why they're magnetized unless there's some residual charge that didn't get made into it. Most of it's neutron, but you have some floating electrons around there, and when a charge moves, it produces a magnetic field. So there has to be some charge there, not all neutrons, and they form this magnetized neutron stars, and since they're rotating and magnetic, if the magnetic pole is this way, then later is this way, and then later is this way, we see that as a pulse. Positive, negative, positive, negative, positive, negative. And that's what makes a pulsar, pulsing star. Okay. That's those little massive stars, okay? Their core, the core, innermost part, is 1.5 to 3 times the size of our whole sun. Really big stars. But whatever. The remaining bigger ones than this are when the remaining core are greater than 3 solar masses. These are huge things. Their gravitational collapse overwhelms everything we understand. We don't know what's happening there. I'm sure there's bunches of theories, but we don't know. Can't go there, never been there, done that, okay? But we know they happen. Overwhelms all known forces, and not even light can escape.
Then how do we see it?
We don't.
Then how do we know they're there?
Huh?
Then how do we know they're there?
Because something else passes behind them and we don't see it, and then it comes back out in front. So, yeah, that basically is what it is. There's more than that. We sense the mass. These are the most massive things in the universe. So we can tell there's a mass there, but absolutely no light. When you have that much mass, you usually have a lot of light coming out of it, no light. But we also see other things pass on the other side of it, and then you don't see it, but then when they come back out the other side, it's sort of like, a tree, and a light passing on one side, like the light shining. So we do know they're there, but we can't see them. We can't study them. Radiation doesn't come out of it. Nothing comes out of it. It's all pulled into it. So we don't know what's there. But we know they're there. In fact, every galaxy has at its center a black hole. That's what makes it a galaxy. That enough gravitational attraction to keep all these stars going around. We don't know what it's doing there, but we know it's massive. Really, really massive. And even within galaxies, you have groupings of stars. Those are around smaller black holes. And these are called, and we'll talk about this in later chapters too. So, even light cannot escape. That's why they're black. Okay. Completely different reason why they're, the small star becomes a black chunk of coal Well, that's because it's not hot enough to give off light. This is so massive, light can't escape. Okay? And if you thought these were dense, these are incredibly dense, compact objects, and no one knows what happens. There are all kinds of theories. I can tell you like theories, okay?
What are they made out of?
Huh?
What are they made out of?
Everything. Anything that gets close. That just sucks it in.
Sucks everything.
Yeah. Here's one theory I've read or heard, and I don't understand it at all, but there's people out there that think there may be parallel universes, and that maybe when
Star Trek.
say again?
Star Trek.
Star Trek, okay. When stuff gets sucked into a black hole, it may come out in another universe and do something else there. I can't say yes or no to that. It seems pretty far-fetched, but the answer is who knows. We have theories, but we don't really understand them well enough to even test the theories. And you sure can't get close to them. If you do, you're sucked in too, you know. Okay. Oh, now no. I can't tell anybody. No, you're dead. Okay.
So we can, okay. So we can navigate around black holes in outer space, correct?
No, we've never gotten close.
Well, I know, but well, I guess the fun thing is because they discovered these 9 new planets.
Yeah.
With however many light years away, I was looking at that.
Yeah.
So you mean we have the capability of maneuvering around a black hole so when we out doing space exploration, we can't go get sucked in one.
Well, okay. Let's think along those lines. That 9th planet you're talking about, and they have a lot of evidence, mostly because there seems to be a mass out there, but we so far haven't seen it. Remember, planets you see them only because they reflect the light from the sun. Well, what if it's on the other side of the sun so we can't see it and it takes a long time for it to move, talking about more time than recorded history, So, and it would be so faint, we can't even see Pluto. We know Pluto's there, okay? But we've never seen it with your naked eye, with the binoculars. It's the strongest of telescopes that you can even see Pluto. Well, this is way out beyond Pluto, okay? So we haven't reached it yet. But what you're talking about here is our little bitty solar system. There are billions of these stars in the Milky Way, and it's at the center of the Milky Way you get the black hole. No, we haven't come close, okay? We have barely, in fact, we've not reached the edge of our solar system yet. So we haven't gone to the next closest star yet. And if this is our solar system here, and there's the next closest star, the black hole is somewhere maybe beyond that corner. Okay, I'm making some of this up, but you got the general idea. So no, our space exploration, we haven't come close. It's our exploring space through equipment and stuff, sensors and things. That's how we've detected them. No, we haven't been there close enough. But we have seen things go black and then come back again. And the only explanation they've come up with is it went on the other side of a black hole and then came back out. Not back out, but way away from it. Didn't get sucked in. That would come out, but on the other side of it. Sort of like that 9th planet. It's somewhere over there on the other side of the sun, but so far hasn't gotten close enough that we can see any light from it. Or something like that. Okay. Now, here is a I meant to say this. Let's go back a few slides. That planetary nebula, nice, neat little picture, but the one in our book, the new edition, page 363, boy, isn't that a pretty one. And that shows various layers of the thing being blown out. And you see that one little remainder of the core, that white dwarf in the center. Okay? And then this illustration here is pretty tame, isn't it? Compared to the one in your text, if you got the new book, boy, that's a lot neater looking, isn't it? Okay. So this is in color, that's black and white. This is a soon. Okay. So here is where it started. A mass of gases, a nebula. Okay? Not a star yet. No promise of being a star. This is just the stuff that could make up a star at some time. But if something happens that forces, like a pulse or something, a disturbance that forces some of those molecules close enough together, they start sticking to each other, now you start getting gravitational collapse. So you start collapsing. Now, if you remember reading it, let's see one of the captions or something, or maybe that example, the Orion Nebula they mentioned, there are bunches of stars have come out of that. So you don't just get one star out of a nebula. It may be just a little part of the nebula. If it's a big enough mass of gases, will form one star, and then maybe some of the others will form another one later. You know. But anyway, if you have that gravitational collapse, and then you start getting hot enough to start having fusion, hydrogen fusing with helium, now suddenly you start that process to get your dynamical equilibrium again. I want to say dynamic equilibrium, they say dynamical. I don't know if there is such a word. But anyway, this is now a protostar. At this point, that's going to be a star. Not necessarily here. This will be the place that's going to become a star. And then ultimately it becomes a main sequence star. Some of these may be huge, some may be small, they may be hot, they may be cold, cool, but they are a main sequence star. And they live there most of their life. Millions of years, trillions of years, billions of years. Whatever the size and mass they are, that will be. But then, when they get near the end, the low mass stars, that would include our Earth, you get the red giant when the hydrogen fusion ceases. You run out of hydrogen fuel and you go through that process, okay? And it will be red at first, and then when it blows off the outer core, the outer layers of the radiation zone and the convection zone, they get blown away, those gases get blown away. What's left is just the core, and that's a white dwarf. It's white only because it's still so stinking hot. Okay? Very, 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 very hot. Okay? But then there's no more fusion, so it will lose its heat over how many hundreds of thousands of million years, they don't say. But over time, there's nothing else to keep it hot, so it loses the heat and becomes a cold lump of carbon.
And then when it falls to the earth, it becomes a meteorite?
That lump of carbon, if that's the core of a previous star, even a small star, we don't want that colliding with the Earth, no. Okay? Because that would be, that would be way. That's just floating around. And a later, is it this chapter or a later chapter? Yeah, it's this chapter. You will see a whole page on page 371 called dark matter. That becomes just some of that dark matter out there in the universe. Okay?
Armageddon.
What's that?
Armageddon.
Well, yeah, if that were to come in, that would be problematic even for the sun. For us, it's like a slit. Yeah, so no. What we're talking about, the stuff that hits us and stuff, that's left over from little old comets and asteroids, small things. So we hope we don't run into any of those ones. Even from the smallest star, that would be way too big for us. Okay. Stay away. Okay. Now, the mid-mass stars, and maybe we fall in here, then they become a red giant as they're exploding, as the inner core is collapsing again. When it reaches a high enough temperature to reach helium fusing the carbon, then it enters the main sequence again, but it doesn't stay there very long, because when the helium's used up, then it collapses again and rebounds, and that's your planetary nebula. There goes your outer layers, and you're only left with the core, and that's, of course, still not big enough, so it's still a white dwarf, and it winds up there. It just moves over time. Okay. Now, I don't know why, to me, they got these backwards. They ought to have this one below that and this one up here, because this is the next most mass. This is the smallest, mid-size, high mass, but this is low high mass, and this is high mass. Why did they flip them up? And not only that, in the book they did the same thing. They show the black hole between the white dwarf and the neutron star. Hey, it's not. It should be reversed from that. Okay? So this time, when the hydrogen is used up, you get the red giant. And then when the red giant goes through it and does helium fusion into carbon, and then it collapses again and does carbon fusion all the way up to or including iron. And then everything's used up in normal fusion. So that collapse is an enormous collapse, and when it does, it rebounds into a supernova. That creates enough energy to fuse higher elements. So that's where you get your gold, platinum, silver, lead, all those bigger elements come from supernovas. Now, the less massive of these, they're still huge masses, they become neutron stars. The most massive of these become black holes. Why they have those, to me, in reverse order, I don't know. But they do in the new picture too, the pretty picture. Okay. Now, if you look at that protostar in the pretty picture in the book, and you see it here too, you see there's a lot of stuff floating around because it's not reached its equilibrium yet. It's doing this kind of stuff, and stuff is getting blown out. Thank you very much. This is where planets come from. That unstable. Once it became the main secret star, it's not spewing out material to make new planets or anything. That's what this is happening. And this is where we came from. In your picture in the book, you can almost picture those planets circling the star. Later, they just show the star and don't show the planets. Okay? But that's sort of a key there. And some of the junk that's flown out there, that then becomes your shooting stars.
You said that's how the Earth developed.
What's that?
That was you said.
Yeah, this is where the planets come from, some of this stuff that gets blown out here as it's trying to equilibrate. Yeah. Now, we'll talk about that in a later chapter. Yeah. That's where we came from. Yeah, right. Okay. Now that's stars, okay? And I think we've hit most of what's happening in a star. Your book has a great picture and probably a better description of pulsars. That's on page 364. So since you were asking about, somebody asked about that, there it is. They say very strongly magnetized neutron star, but they don't say why it's magnetized. Magnetic fields come from moving charges, so there must be some free charges there that are spinning around that neutron star. Okay. All right. Trying to make sure I'm covering everything they show in the book. There is a closer look on observing with new technology, and they're talking about all the different ways. Now, this goes back to your question, too. How do we know it's there, and stuff, if we can't see it and visit it and measure it? These various things, they mention astronomers, new technology has helped astronomers use to observe evidence of stars in all stages, from protostar to black hole. That technology uses infrared, which is heat sensing, X-rays, which is high energy cosmic radiation, gamma rays, which is even higher energy cosmic radiation, radio waves, which is very low energy waves that you do, and all these things you can see through dust, bright lights, and other problems that make observation difficult when you use visible light only. So, and then they show some of these devices that have been sent into space, so you don't have to worry with our atmosphere. And these are collecting data that we wouldn't be able to distinguish here on Earth. And they send back the data. So X-ray telescopes, infrared telescopes, gamma ray telescopes, radio telescopes, and another radio telescope. But they measure different frequencies, different energies, and things like this. And they get all this information, they build the models, and they see what makes it fit and what doesn't work, and finally they come up with a few suggestions, theories. We don't know for sure. That's the final answer. Now, we talked about earlier light pollution. There's a good little blurb on Science and Society at the top of page 365 on light pollution with a few questions to think about, so well worth your time to do that. There is a neat picture. It wasn't in the earlier editions. It is in this one, figure 1415 on page 365. It's pretty incredible looking. A jet of particles streaming out of the center of galaxy M87, that says nothing to me, at nearly the speed of light. Now wait a minute. Particles moving at nearly the speed of light, that's almost unheard of. So it must be really big stuff happening there. The jet is powered by a monstrous black hole that is estimated to have swallowed up matter equal to 2 billion times our sun's mass. Okay.
Wait.
Yeah, exactly. The numbers are just astronomical. Okay. And I don't know. It swallowed it. What is this jet of stuff coming out? Did it belch? I don't know. I mean, who knows? And maybe this is what happens when black holes get too much. Something comes spewing out. I don't know. I do not know. Okay.
How come we're so knowledgeable about everything not?
What's that?
Why do we have so much knowledge of what's out there except the black hole?
Well, I mean, we know a lot about it, but
How can we know so much about it then if we can't even see it?
yeah, because we have all this data coming in from all different kinds of energy spectra and things like this, and they piece together, and a lot of it's theory. I mean, they say, well, of models, what could make this happen? We'll try this. No, that won't work. Ooh, this seems to work. Now, whether we got enough data we don't have enough to prove the theory, but at least it fits everything we know so far. So that's what we know is, maybe it's not really know it right, but it's the best one. It's our best guess. What's that?
Sort of like when we thought at one time
the Earth was flat, exactly. Or that having babies lay on their stomach rather than laying on their back. No, lay on their back rather than lay on their stomach. Yeah. Or I've been reading some historical novels and stuff. One of the main ways that doctors used to treat people? Bleed them, because they have these humors in their body and you need to get them out. Well, you weaken them and they died. Well, we didn't get it in time. So I think George Washington, I'm pretty sure, was bled to death. I mean, they won't say that. He had some illness, but they were trying to cure it with bleeding, and it weakened him. I mean, it may not be him, but I bet you it's happened way more times. So who knows what people will be saying about us in a few 50 decades or hundreds or millennia or whatever way they say. Did they really believe that? All right. Let's move on to larger structures. Most of what we've been talking about are stars. That's 14.2 was all about stars. Now let's move to the larger scale structures. And I think I mentioned this before. Most stars in the universe are not unitary stars. We just happen to be floating around one, okay? We may think all stars are like our star. No, most of them are binary. Two stars that rotate around each other, okay? Binary meaning two. Yeah. Okay? So, two gravitationally bound stars that do this, okay? Now, not only that though, we sometimes have collections of binary or unitary stars that are hanging around each other. These can be tens, and this is not really very clear, but I think they mean tens to hundreds of thousands of stars. I don't think they mean tens of stars to hundreds of thousands of stars. That may be what they mean. I think they mean tens of thousands to hundreds of thousands or more gravitationally bound stars, and these are called star clusters. Now, there may be a little black hole in the middle of that that's holding them there. But that's a little black hole. The one at the center of the universe, that's a massive black hole. Okay? Often these share a common origin. Remember I mentioned the Orion Nebula is a, what do they call it, generator for stars. I mean, that's where bunches of stars are currently being formed. Some are in protostars, some are main sequence stars, some are just masses of gases. But there's enough gas out there, and when all of them get formed, they will probably stay as a cluster around each other. Part of the galaxy, but they are a cluster of stars. Okay? And then we have galaxies. Now, you might think, we probably have thought before, planets are the main feature of the universe. Planets are little specks of dust, okay? So you might say, stars are the main unit of the universe. No. The main unit of the universe is a galaxy, okay? It's made up of these little other specks, okay? Flecks, okay? But a galaxy is billions and billions of gravitationally bound stars. Some of these in star clusters and other things. So we have that's the main unit of the universe, okay? But we have clusters of galaxies, okay? I think Andromeda and us that's our closest galaxy to it. There's a dwarf galaxy somewhere fairly close to it that we seem to be sucking in and probably will become part of the Milky Way before too long. That may be trillions of years from now. Yeah, just a little while. But there are superclusters of there are clusters of galaxies, and then superclusters of galaxies, and then there's billions and billions of galaxies out there. Does that make you feel small? If we are a tiny speck of dust compared to our sun is a medium-sized star in a galaxy of billions and billions of stars, the Milky Way, and we are part of a cluster of galaxies that could be bunches of them, and then superclusters of galaxies, and then you have billions and billions of galaxies. I'm lost. Okay, I cannot conceive of the dimensions you're talking about there. And that came from one Big Bang? I don't know. Goodness gracious. Talk about a Big Bang. So let's talk about our galaxy. I can't get on those others. The Milky Way. Now, have any of you ever seen it? Have you been in a place that's clear enough at night that you can see that sort of streak? And how it got its name, they said it looked like someone spilled milk across the sky. And that's why they called it the Milky Way. Because, frankly, it are so many stars, such tiny little stars, but so many of them so deep that it obviously is a pattern of spilt milk. Okay. Diffuse span on a dark night. See if he knows how to keep a secret. There are billions of stars, and some of these are bound in, I think they mean here, star clusters. in the Milky Way there wouldn't be galactic clusters because we'd be part of a galactic cluster. I think they mean star clusters. Okay. What's the structure of the Milky Way? Now, get used to this. Very similar to a solar system, or sort of similar to it. Okay? You have a galactic nucleus. Okay? That is one massive grouping of stars. I mean, and they're not really close together, but on the scale they look like they are. A huge galactic nucleus, and then around that is a galactic disk. Okay? And in that disk are bunches of stars there. Now the disk is sort of like a pinwheel type thing. The diameter of our Milky Way is about 100,000 light years across. Okay? So talk about exploring space. To drive from, to go from one edge of the Milky Way to the other edge of the Milky Way, for a light beam to go there takes 100,000 years. Traveling at 186,000 miles a second, it would take 100,000 years for a light to go across our galaxy. We haven't explored that much, okay? Okay. Now, there is also what they call the spherical galactic halo, okay? And this spherical galactic halo contains about 150 of these globular clusters, which are smaller clusters of stars that probably have little black holes or something, or they were just formed together, and they are all around there too. They're not necessarily in the disk, but they're around it. So let's get a picture of that. Well, first, here's a picture of the Milky Way. Your picture in the text is actually it. Both of these are pictures. That's a picture taken through a telescope, I think. This is one taken just of the night sky in a very dark area. Okay? This is, okay? And this is what the Milky Way looks like. Okay? Now, that's a very dark sky with no light pollution at all. And I think it's taken through a telescope, so I've never seen it look that bright. What are we looking at then? Here's my guess. Here is your galactic nucleus here. I mean, tons of stars there. Okay. Now this is looking at it from above. This is looking at it from the edge. This is your halo, galactic spherical halo, and these are all globular clusters of stars that are not part of these spirals. Okay? This is where the nucleus is, and somewhere in the middle of that is the huge black hole that is keeping everything spinning around it. Okay? We live right here. Okay? So when we look and see the Milky Way, we're probably either looking that way or that way. We don't have a chance to see anything here. I'm not even sure we can see anything in the next adjacent spiral. We're just looking one side or the other. Okay? I think. You see maybe a few of these up here or something, but that's all you see. Okay? So, no, we don't have a clue. Okay? It's incredible. All right. Now, remember this picture. When we talk about our solar system, our sun will be a lot like this. And rather than being spirals of things, the planets are in orbits around it. But then you have comets and other things all around here. Yeah, all the planets are within here and here, but then you have other stuff here. Just hang on to the concept because you'll see it again. But the scale is way, way different. Okay. Now, that's our Milky Way. How about other galaxies? Okay? And by the way, before I pass it in the book, there is a nice little blurb on extraterrestrials. Are any of you old enough to remember extraterrestrials?
E.T.
E.T., exactly. Okay? The likelihood of that really happening, that, folks, was big fiction with a little science, okay? Science fiction with emphasis on fiction, okay? And they do a pretty good description of how unlikely it would anything would be this. Well worth a read. Closer look there on page 366. Across the page from that, there is a people behind the science, Jocelyn Susan Bell Burnell. Boy, does she have enough names. Now, I don't know if she's still alive, but as of 2003, she seemed to still be alive, and maybe she still is today. But she was the astronomer, female astronomer, who discovered the first pulsar. Pretty impressive, okay? Well worth a read. Now, is this your source if you choose to write on her? No. You have to get a source outside the book. This gives you the idea, but don't just, I've read this before, and if you write it down again, I'll say, I know where they got that. They didn't go outside the book at all, okay? You need to go outside the book and find out some other stuff. Okay. Well worth a read, though. Now, other galaxies. That's where we are now, page 368. I was just trying to catch up. Our nearest neighbors, now we're not talking about the nearest star. Nearest star to us is, I think, Alpha Centauri. It's a fairly small star, and it's only a few hundred light years away, probably. I mean, but the nearest neighbors to our galaxy is something called the local group. Really clever name. It's about 1,000 light years in diameter, as opposed to Milky Way, which is 100,000 light years in diameter. So this would be a pretty small, a dwarf galaxy. The nearest dwarf galaxy to us, we think, is being disrupted gravitationally by us, the Milky Way, and probably is going to be sucked in to us at some point. Now, what does that mean? I would guess it means some of these will get a little longer. Okay, that's the only thing I can imagine. It's just they'll be brought in and sort of added to our spiral out there or something like that. Okay, that's my guess. That's not science. Okay. Now, the next closest galaxy is Andromeda, which is almost our twin. I think it's the bigger twin. I think she's a little bit larger than we are. It's 2 million light years away from us. Okay? We can see Andromeda out there. Okay? There is a constellation named Andromeda. It's named after some Greek story. Yeah. What's that?
I know the Greek story.
You what?
Oh, I know the Greek story.
Oh, you do? Okay. How does that go?
Andromeda was a Greek princess who was rescued by Perseus, the Greek hero,
Right.
from the giant water source.
Yeah, he was like a water guy.
Right. Yeah. And that's why the Greeks, the positioning in there, Perseus is pursuing but never reaches Andromeda or something. Yeah. If we go to the planetarium, there's a chance. He doesn't do it every time, but sometimes he tells some of those Greek stories about things, and it is pretty interesting. Well, one of the stars in that galaxy, and this is why it was named Andromeda, because the Greeks had already named the constellation Andromeda. They found that one of those stars isn't really a star. It's a whole galaxy. But it shows up as a pretty dim star because its light came from 2 million years ago. Okay. Now, here's the thing, one of the things I find really fascinating to think about. But remember, it takes, the lifetime of stars is measured in millions of years to billions of years to trillions of years. But it could be that when we're looking at that little twinkle, twinkle little star up there somewhere, it may be, it's so far away, okay, say it's in our galaxy, and say it's 1,000 light years away. That's a really close, okay? 1,000 light years away. Well, it could be that star has already become a black lump of coal, but we're still seeing the light that it sent 1,000 years ago, but it's already died since then, you know. So we're looking at a star that may not be there anymore because we're seeing light that came from 1,000 years ago. Duh. I mean, it's just sort of scary to think about. All right, but that's Andromeda, 2 million light years away, very similar to Milky Way. And in your text, there is a picture taken, I think, from the Hubble Space Telescope and blown up like crazy. That's how our galaxy looks probably to them, too. Okay? Now, you may have heard this name before, Hubble. Hubble has probably become the most preeminent astronomer of our times. Okay, I think he's dead now, but they named the Hubble Space Telescope after him. Okay, that's where we use the name a lot. But there's Hubble's law, there's Hubble everything. He came up with the classification scheme of how to classify galaxies. There are some galaxies they call elliptical. That means they have a minor axis and a major axis. We are a spiral galaxy, as is Andromeda. There are some that are barred galaxies that seem like the stars go out in spikes or bars from that. And then there's those that you couldn't classify any other way. You call them irregular galaxies. They're just sort of out there, you know. Like a picture I would draw would be very irregular. Okay. Now, why would that be? Maybe their central black hole is not as big as some of the others. I don't know. Maybe there's 2 or 3. Maybe in those elliptical, there's actually 2 black holes, and they're going around. You know, who knows? I'm just guessing. Okay. There is the picture of Andromeda. It's a slightly different take on what we saw in your book, but there it is. Now, this is taken at such great magnification, I would almost guess that maybe another galaxy somewhere way, way back there, and here's yet another one. Or at least a galactic cluster or something like that. Well, we're back to full attendance from everyone who's been here is back here. That's good to see. I thought I'd chase people away, but I guess they came back. Okay. So who knows? I'm just sort of guessing at it. It'd be interesting to do. The one in your text shows a slightly different take on it, and I bet you some of those brighter things back there are probably other galaxies, but I don't know. All right. Now, they have and I don't see anything. Yeah, okay. On the slide set, this is called The Life of a Galaxy. In the text, the topic is called The Universe, which I thought was the name of the whole chapter, but it is. Oh, and by the way, there's a nice little blurb here, Myths, Mistakes, and Misunderstanding. Someone mentioned Star Trek, didn't you?
Yes, sir.
Okay. All right. Remember, Star Trek was supposedly this spacecraft that was going, I think they stayed within the Milky Way, didn't they? I don't think they went to other galaxies. Did they?
Yeah, they always went to other galaxies.
Or did they? How, say again?
I said they always went to other galaxies.
Okay. Okay, let's see how real, but they always got their orders from Starfleet Command, right?
Yes.
Okay.
Yeah.
So let's just assume Starfleet Command was on the Earth or some other planet in the Milky Way, right?
Yeah.
Okay. Now, if they were just talking, Starfleet Command, say, located on Earth, was talking to Mars, it would be 4.3 minutes in between every transmission. 4.3 minutes for you to get the message from Mars and Mars to get the message from you. So a total of 8.6 minutes. Okay? Jupiter, 35 minutes. By the time you had sent a message to Jupiter and got the answer back, you're over an hour. Okay? Saturn, 1.2 hours to get the message there, 1.2 to get it back. 2.4 hours around, to complete one exchange. Okay? Uranus, 2.6 hours for one way, 5.2 hours for the complete conversation. Neptune, 4 hours there, 4 hours back. That's a full day. Hey, how are you doing? Fine, how are you? That takes all day, okay, to get that. Pluto, 5.3 hours on average. One way, 10.6 back. Across the Milky Way, our galaxy, 100,000 years. Because communications travel by electromagnetic radiation. Light is just one form of that. Okay. So guess what? It would have been generations of Captain Kirk's to send a message to Star Trek if he was from Andromeda. 2 million years. One-way message. Get an answer back another 2 million years. What was the question? Yeah. I don't remember. That was my great. Well, how many grandfathers away? Ask. Okay. I think that was more fiction than science. Okay. I love Star Trek, by the way. All right. So, now let's look at the universe in the text, which is Life of the Galaxy on the slide set. This is not the TV show. That's definitely more fiction than science, okay? In fact, it's hard. Well, actually, of all the shows on television, it probably has the most science of any of them. But then there's all the fiction with it, too. Okay, but really, they do try to get the science close to right, amazingly so. But the Big Bang Theory is just the most recent current guess of how this all got started. Nobody knows. The trouble is, no. Okay. But the theory is, and here's why they think the Big Bang may be what happened. Or this is what they think. The universe evolved from some explosive beginning. Now think about what the universe contains. Our galaxy contains billions of stars. There are billions of galaxies. I mean, all this started with one collection of something blowing outward. Wow, that was big. Big bang. Okay. Now, what is the supporting evidence? Now, this leaves me pretty empty. Microwave background radiation. What? Well, no. These are things they've collected, and everything they collect, the only way they can say, why is this coming in this way, is if something like this happened. Another, and this I can understand a little bit more, large-scale expansion. Now, we've known, oh, this sounds so silly. We've known for years, when you consider the life of our sun has already lived about 10 billion years, so when I say, oh, we've known for at least 20 years, what is that compared to how long ago this stuff was supposed to happen? But as people have been studying it, they know that the universe is expanding. All the evidences do. So that's what they mean large-scale expansion. Why would we be expanding? It must have been a big bang at the beginning. Okay? That was the theory anyway. Now another, the relative abundances of the elements. Now remember, just from fusion of stars, big stars, you only go up to iron. But, you know, most of the elements in the Earth, iron and below. The other thing is what makes them so valuable, they're very, very rare. Golds and silvers and platinums and uranium and things like that. Very low abundance of those. But the fact that we have them indicates there must have been something much bigger than just normal fusion. Okay, because that would have only gotten us up to iron. Okay, and then, this leaves me pretty cold too, diffuse cosmic background radiation from the Kobe spacecraft. Okay, well, if you read up on that and find out, and by the way, just about any one of these would be a topic in itself if you wanted to write on this. What is the Kobe spacecraft? That could be spacecraft. Okay, but all the things they collected support the idea, yeah, there must have been a big bang. Now, they don't talk about it in this slide, but it is other place in the book. Here's the part that even baffles me more than this. Yeah, I can see that if there was a big bang at the beginning, that everything would have been thrown out there, right? But from our knowledge of physics, the best it could be doing was expanding at a constant rate. Okay? Okay, the best it could do. But what they've discovered, and Hubble was part of this too, it's not just expanding, the rate of expansion is accelerating. And from physics, we know acceleration only comes from a net force. Something is pushing us out, not just that there was a bang and we got thrown out there and we just are going out at a constant speed. We're accelerating. Something's making us go faster. What in the world is that something? Do not know. And here's the question. What is the end? Do we expand forever? Well, right now, if we're accelerating an expansion, that seems to be it. Now, maybe the acceleration is only going to last so long, and then suddenly, then at some point, it will become constant. And then at some point, it may start coming back in. So either it's expanding forever, or it's like a spring, and at some point, it's going to come back, and then you'll have a big crunch. Or if you talk about a bang, that will end in a bang. Okay, never mind. Okay. All right, yeah, that's lots of fodder for science fiction, isn't there?
Oh, yeah.
Will we need to worry about it if we're still expanding now? I mean, if you think about how a spring works, that's how simple my mind is. As long as you're going toward the equilibrium point, you are accelerating, okay? When you reach the equilibrium point, you quit accelerating and there's no acceleration. Then when you go past that, you start slowing down. So you start decelerating. And that's why it goes like this. So if but you see, we're going away from something, not towards something. And I can't figure that one at all. But if that were the case, are we going to go away so long, then slow down? Is the rate of acceleration going to slow down, finally stop, and then start coming back? I don't know. But if we're still in the process, and it's been 13 billion years or something like that since we think it started, I'm not going to worry about it. Okay? I think I'll be long gone before any changes are evident. Okay? I don't know. It's interesting to speculate. Lots of potential paper topics here. Here was an early model that they used. They call it the raisin bread dough model, or something like that. That if you are making bread, raisin bread, and you mix up the dough and you have the raisins fairly evenly spaced in the dough, and then you let it rise, all the raisins are getting further and further away from each other, right? That's the model that we're living under. The question is, what kind of yeast is that? That's actually expanding at a accelerating rate, not begun to slow down yet. But that's one model. Okay? Now, this is, they don't have this figure, so to speak, in ours. This is another way of saying that. If originally there was a Big Bang, whatever that was, and then it sent all these billions upon billions of galaxies flying away, and now they're flying away from each other, and here's the scary part, at an increasing rate, this is what's occurring. Now, I've read and heard someone say they think Andromeda and us are actually on a collision course. And I thought, how does that fit with this? Because if we're supposed to be moving away from each other, how are we colliding? I don't know. But they say there's so much space between the stars and everything else that even if it were to happen, they would just go right through each other, and neither one of them would be disturbed at all. I can't figure that. Yeah, that's what I said. What? But that was one of the theories. So I don't know. There's so much out there that we have no clue on. Okay. Now, sort of to follow up your question, Cece, how do we know so much? There are many ways that we know less about what's under our ocean than we know what's in outer space.
That's what I was thinking. I was like, why don't we actually study what's at the bottom
Yeah.
of the ocean before we go expanding somewhere else?
I say study it all. I don't know. All right. Now, I think that's the last slide. But there are several really good features in the text. One on dark energy. Now, that to me is a strange term. And I think that's why it's a strange term, because no one can figure out really what it is. They are able to know that the energy is there, but they can't really measure it. Or, it's so bizarre. Nice little blurb, but not quite half a page. Okay? There's a couple of examples here which it's sort of like they threw in just to have something to throw in. There is an equation listed here. It's Hubble's law. I told you Hubble was all over the place here. That V, I believe that usually is velocity, but I don't see it listed here, is equal to Hubble's constant, 21.5 kilometers per second per million light years, I think that term is. And this is describing the expansion of the universe, I think. Okay? The other earlier text didn't have that, but here it is, so take a look at it. And then I think those two examples use it. But again, it's sort of like they just threw that in. And here is something right on page 370. Good question. How old is the universe? As mentioned earlier, astronomical and physical clocks indicate they think the universe formed with the Big Bang some 13.7 billion years ago. Expanding, and they go on about this. They give temperatures and things like this. It's just absolutely amazing, the numbers you're talking about. Now think on this too. We think our sun is about 5 billion years old. So that means many supernovas could have happened between the time of the Big Bang and before our sun was even started, okay? Because the most massive stars only live about a number of millions of years, and you're talking about 8.5 billion years in there. So we could be well on the way, but we still seem to be increasing. So It's amazing. Then there's almost a full page on dark matter. It's worth a read. It's not particularly easy reading, but I think it's really, it just shows some of the depth of stuff that we don't understand yet. And then there's one more. There's a possible models of the universe, and they showed 3 possible outcomes. This is on page 372. Given the universe's density, it will either begin to collapse, cease expansion, or continue to expand. Okay, that covers it all. Okay, it's either going to continue to expand, stop expanding, or collapse. Yeah, I can't think of any other options than that, but and these again are models of things they think could happen. All right, that's the chapter. And I'll say this every chapter, and I truly mean it every chapter. Nothing replaces reading the book, okay? But once you have it read, the summary does a pretty good job of highlighting the most important things in there. They have these equations, and these, I didn't even notice the first 2, I just noticed the last one. Don't sweat these too much. We're not really using those much. I'm not using them at all. But the key terms here, for most chapters, this is sort of a short list. The summary is about normal, maybe a little on the short side, but it's a fairly short list. Now, the key terms are listed alphabetically, but they give in parentheses the page number where they were first defined or mentioned or described, so you can find those pretty well. I think, this is just my personal belief, the very best thing to study for a test is applying the concepts. I mean, read the chapter, that's the best, and go over the other, but this, at the end of the chapter, applying the concepts. It's 50 multiple choice questions. Now, the maximum, I think, on any test in this course is not much more than 20, usually fewer than 20. So this 50 multiple questions, you will not see the same question on the test, but the material that the question is covering, you'll see some of those on the test. It just may be asked in a different way or something like this. So you have 50 multiple choice questions and the answers given. Okay? So try your best at working those, compare those with the answers. If you can't figure out why your answer is different from theirs, most of the time you say, oh, it said that one, then go back and read, oh, I see why, you know. That's a good way to study. If you can't possibly figure out how they got this answer, please bring it to class, and we'll address those. I may not be able to figure it either, okay? Because this is a new addition. I don't know if any of these questions are new ones I haven't seen before.
So is our notes not going to be good enough for us
What's
to
that?
study for our test? Just our notes?
Oh, they'll be good enough,
Because,
for sure.
I told you I ordered my book.
Right.
I don't know when it'll be here.
Okay.
I mean, hopefully it'll be here for Tuesday, but if
Yeah.
not...
If not, yeah, I mean, that's going to be adequate. But if anyone wants to come and take a picture of my book or anybody else's book, these have the answers in them, so that's, 3 pages. You can do that. Okay? Let me go over the rest. Questions for thought? Man, there's a lot of these, 21. And well worth thinking through these. Again, they rehash the same type of stuff. For further, and that's a bit more than normal chapters, I think. For further analysis, there's 5, that's about normal. And then there's an invitation to inquiry. It has several things there that you might want to consider looking into paper topic. For instance, Pioneer 10, a spacecraft. When you talked about Hubble Space Telescope, when we talked about the COBE, when we talked about all these other things, any of those would be a potential paper topic. Then there's parallel exercises. These are like the examples in the book, which some of them were sort of made up. If you don't get turned on by those too much, don't sweat it. I'm not going to give you any calculational problems on the test. But some of these may be things you'd be interested in, and they may give depth to what you studied in the test. Okay? So
you recommend, like, the key terms?
well, what I said, the applying the concepts. The key terms are pretty good things to look at too, but the applying the concepts I think would be the most bang for the buck. But the thing is, you probably almost need the book to say, why is this answer true, you know? But at least you can see what the correct answers are. Or at least I say correct answers. In the earlier editions, usually I'd find maybe one or two every chapter now or then that might be wrong. Most of them have been vetted pretty well. I would hope this edition, they got them pretty well. Okay. Any questions then on chapter 14? And you're welcome to use my book or any other book to take any pictures you want. Now, we got about 30 minutes before it's lab time. Do you want to take a little quick break now? Then we'll come back, finish chapter 15, and move straight into the lab. Start chapter 15 and move straight into the lab. If you want to do that, then I'm going to pause the recording for a moment here. All right, where we're going to start off now, and we won't have time for much, but let's look at chapter 15, the solar system. Okay? I feel like I got a sneeze, so hopefully I won't, but you'll know if I do. Okay. There is a pretty nifty picture in your text, if you got your text, and this was different from the one that's projected on the board here. It's a self-portrait of NASA's robotic lander Curiosity in the Gale crater from a surface of Mars. The base of Gale's crater is 5 kilometer, which is 3 mile high mountain, Mount Sharp, rises 3 miles high, okay, rises on the right side of the image. That's what you see over there, okay. So this is sort of like their selfie, you know, the rover took a selfie of itself. Okay, pretty incredible. So we're going to talk about the solar system. Starting with the universe, now we're going to narrow it down to the solar system, and then the next chapter will be Earth-Moon system, and we'll be through with the astronomy portion. Oops, did you get it? I'm sorry, I didn't mean to. You did? Okay. I didn't know you were taking it. I just caught a glimpse of it right as I clicked it. Here's the core concept, okay. I think it's the same. I usually check just to make sure they haven't changed anything. Because, like I said, this is a newer edition than the slideshow. The solar system is composed of Sol, meaning sun. Okay, that's where Sol comes from. Sol, okay, sun. Okay, and orbiting planets, a few dwarf planets.
What are dwarf planets?
Okay, good question. Those are bodies that orbit the sun that don't fit the characteristics of what they determine makes a planet. I mean, that sounds like a circular thing, but you see there's a body called IAAC or something like that that determines the criterion to be named whatever. And they also name things, like they name that crater on Mars. This is the international body. It's an international thing, and they decide, well, to be a planet, these characteristics have to be met. And dwarf planets are, number one, they're smaller. Number two, their orbits are probably not quite right. There's a variety of things that can kick them out. Pluto used to be called the planet. And when they came up with a new set of criteria, they said, hey, Pluto just doesn't fit this. So they named it a dwarf planet. So they're things that circulate the sun, too big to be, well, okay, so I'll say this. You know what the asteroid belt is? If you don't, we'll get there. But there's actually 1 or 2 dwarf planets in the asteroid belt. They're not big enough to be a planet, but they're too big to be just a chunk, of rock or something like that. Pluto is way out there, and it's a dwarf planet. And it'll we'll talk about a few of those, not too much detail. That's what dwarf planets are.
But okay, you said it's still a planet, right? I mean, not. I'm getting when you say like, you said it's not a planet, but it's a dwarf.
A dwarf planet, meaning it doesn't fit the characteristics of the other planets. Okay, it's okay. This just gives you a little bit of an idea. Pluto is smaller than about at least 5 to 10 of the moons that go around other planets. So should it be named a planet when it's that tiny? You know. Another thing, its orbit is wacko, okay? Whereas the other planets are fairly regular orbits, okay? There's just several things that, yeah, it goes around the sun and it's a fairly large object, but it doesn't fit the criteria of other planets, okay? So it's called the dwarf planet. It's sort of like, well, let's see. On the edge of my mind, I can think of something else that uses a very similar word, but that doesn't quite mean the same thing. Second? Midget? That wasn't what I had in mind, but it would be more like, goodness. I can't think of an analogy for that, but it would sort of. All right. It's sort of like if you came here to Lawson, you're taking regular classes for credit to go to college, to transfer to a 4-year school, or to fulfill your requirement for an associate degree, or whatever. Okay? But other students at Lawson may be only taking a 2-day course over at the Continuing Ed Center or something like that. We're all students at Lawson, but they're not the same classification of students. You're degree seeking, they're non-degree seeking. Okay? So you're a college transfer, they may not be college. Yeah. So it would kind of be that kind of thing. They're not really a full-fledged degree seeking student here, but they are coming to Lawson. You know, that type of thing. So a dwarf planet is not quite like the other planets, but it's still going around the sun, kind of like the other planets. That's a lousy description, but. Huh?
I understand.
Okay. All right. Now, this picture is totally misleading, I think. Okay? One thing that's sort of good about the picture is the relative size and certainly the order of the planets are correct. That's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay? Do they ever line up like that? Never in a billions upon billions of years would they ever line up like that. So that's one thing. The relative sizes of them is not too bad. Okay? Relative size of them. The spacing, well, the line up, that's ridiculous. Okay? The spacings are way off. This looks like they're almost evenly spaced. They're not. Okay? In fact, the distance between, we'll get to this a little bit later. You'll see how far off this is. And then the size relative to the sun is nowhere close. I mean, if you did the sun in its proper perspective, the planets would look like these little specks down here. So there's several things wrong with the picture, yes.
Would you say a dwarf planet is kind of the same thing as a dwarf star? A dwarf star is a typical star that you see in the night sky, or it's part of the galaxy?
Okay, I'm trying to think what the actual definition of a dwarf star. We didn't talk about that. Is that from something you've read otherwise?
No, it just made me think of the dwarf planet,
Yeah.
the dwarf star. I thought they had the same concept, even though dwarf planet is what you say. It's not typical planets.
Yeah. Well, yeah.
I think you need to touch on dwarf star.
No, we talked about
talking about something that's something you were saying. It was something about stars when you said.
Okay. Oh. Okay.
Yes.
Okay. Okay. The white. Okay. Okay. I got what you're saying now. That is what used to be a star, but it's at the end of its lifetime. In that sense, no, that's not the same as this. These are just chunks of stuff floating around the sun that never have been like the other planets. Okay. In fact, the planets themselves are very different. In fact, another fact, the Pluto, in some sense, is more like the inner four planets than it is the outer four planets, and yet it's out here. So you see, it just doesn't fit the pattern of the regular planets. Whereas a white dwarf, that's what you were talking about. Okay.
You talked about dwarf galaxies.
Yeah, dwarf galaxies. Okay. Yeah.
And white dwarf was a type of star? A stage of.
Yeah. Yeah, I think, yeah. Yeah, a white dwarf is the end stage of what used to be, like our sun will one day be a white dwarf. So in that sense, if that's what you're asking, no, it's not. It used to be a planet, but it's deteriorated till it's not a planet. No, that's not it. It never was like the other planets. Okay, but the reason they call it dwarf, remember, what makes up a white dwarf star was just the core of what it used to be. Okay, and that isn't the same here. Okay, this was just small to begin with. It always has been small. Okay, so we'll get to those later. But yeah, a dwarf planet is just something that's not quite a planet. Okay, it's like it has some features of planet, but not enough to be called a planet. All right. Now, and other small solar system bodies. Now that would include the asteroids, which we'll talk about, the moons that go around planets, not around the sun, but the planet goes around the sun. Comets and other things like this that are out there in our solar system, but they're doing their thing, but they're not the same as planets or even dwarf planets. Now, with the exception of two of the dwarf planets are in the asteroid belt, so they could be classified asteroids too. All right, so let's look at this. Here it is, the IAU. I couldn't remember it. The International Astronomical Union is the governing authority over the names of celestial bodies. Okay? And for instance, that picture we were just looking at, the Gale crater. Okay? They approved that crater on Mars would be called the Gale crater. Okay? That's what this body does. But in addition to naming things, they classify things. So they define things. The IAU defines what is a planet and what's not. What is a dwarf planet? Okay? What are your classified as an asteroid? What's classified as a comet? What's classified as they determine the things and then decide, and they set the criteria for them. And it just turned out that after they revised the criteria for planets, it turned out Pluto didn't fit enough of the criteria. It couldn't be called a planet. So they reclassified it as a dwarf planet. That's, just another thing. Okay? So in 2003, Pluto was redefined to be a dwarf planet according to the IAU definitions. They set those in place. And then when they evaluated Pluto, it just didn't meet the criteria. Okay? I'm thinking of some concept where you talk about something or a conditional something. And I just can't think of what goes with that. It's flown the coop, but, it sort of seems like it, but it's not quite the same. So, yeah.
I know, this might sound stupid, but if Jupiter is not small enough to be not big enough to be classified as a planet, but
Okay, say that one more time.
if Jupiter is not big enough to be classified as a planet, and
No, Pluto.
I mean, yeah, Pluto. Then, I mean, so like, Pluto's last, right?
Pluto used to be considered the 9th planet, and now it's no longer considered a planet.
Okay.
Yeah.
5.
What's that?
3, 4, 5.
Oh, is it? Shucks. Okay. All right, we didn't get very far, did we? Okay. But I'm glad y'all had the questions. That shows your thinking.
You can go back one slide.
Back one slide, for sure. Okay.
Mr. Fowler?
Yes.
You're not from around here, are you? Where are you from?
I was born in North Carolina, grew up in Georgia, but I've lived here in Alabama since...
You have no southern accent at all.
I'm so sorry.
No,
Oh, goodness, she's slapping me, isn't she? Okay. No. I was also in the Navy for 4 years. That probably helped modify it some. What kind of accent do you consider me having?
None, just American.
Okay.
Southern, you're all. Well,
No, not him.
Okay. All right, we'll pick up. We didn't get very far. In fact, we'll probably come back to this slide next time, too, because I want to say a little bit more about the dwarf planets, and it's not going to show up here, I don't think. Well, yeah. Actually, this will be a good place to start. But anyway. Okay. Now, I'm going to pause this. I think I'll end this. All right. Oh, yeah. Let me do this, too, because I tend to forget. But since I'm... Hunter is still here. LaShondra, I'm still learning names and faces, right? Okay. Rachel?
Frogs.
Say again?
Frogs.
I can't hear.
The frogs.
Frog?
Yes, sir.
Science,
Science,
frogs.
frogs.
When we signed up for this class, I think we all thought that like we were taking a physical
Biology?
science with lab. I think we'd be dissecting stuff.
That's biology. Okay. This is physics. Okay. Physics. Okay. All right. Trey. All right. Good. All right. Ray. All right. Good. Jarrell. Okay. Gotcha. Cece is here. I have to do this. I'm sorry. Anthony. Sean. Fred. There you are. Okay. Knew you were somewhere back there. Chelsea. Yeah. Right. Sam. Okay. Nick. Right there. Okay. Got it. Melba. Willie. Got it. Lisa. Oh yeah, there's. I'm sorry. I was thinking a different class. I have another Lisa. This one. Okay. Tiara. Okay, got it. Thank you. Anhil. Ashlyn. And we're just missing Kedrick Deontay Williams. Still haven't seen him. Okay. While I was doing that, hopefully you were reading the first page. Okay? I'm not going to read it for you, but I'll go over a few things we talked about in the last chapter, reminding you that what is the line that's called from due north, goes directly over your head, down to due south.
Altitude.
Altitude is how high something is above the horizon. What is that line? Say again?
Azimuth.
Okay, azimuth is the angle it is from due south.
Celestial something.
Celestial something or another. Okay.
Equator.
No.
There is a celestial equator for that. Meridian! Very good. That's your meridian. Okay. What's that?
So we'll just call all of them out till we get it.
Yeah, that's it. Yeah. I mean, okay. When the sun or any other object crosses your meridian, we say it's a transit. Yeah. So, and when it does, that's the highest point it'll ever be. Its altitude is lower here. That's the maximum altitude, and it goes lower as it goes down. So when it crosses your meridian, that's when it's in transit, and that's the maximum altitude it'll have on that day. Next day it may be different, okay? So, now, what do we mean, and this relates to Monday, what does it mean ecliptic?
Circle.
Say again?
Circle.
Circle?
No,
It is a circle.
So
Yeah.
like what does eclipse mean?
Ecliptic. Okay. That's when the sun gets in front of something or something gets in front of the sun. And we're talking about the sun. So the ecliptic of the sun will be the path it takes over the year. And right now we're in August. And actually the sun every day at noon is a little bit lower in the sky than it was the day before. Okay? Okay? On September the 21st, it'll reach its medium average, and then after that it'll keep dropping until around December 21st, and then at noon it will be the lowest it'll ever be. And then it starts climbing again, and back in spring it'll be the same place it was in December. But the imaginary circle around the Earth that the sun would be eclipsing any other star, that's the ecliptic. The path of the sun is the circular path around the Earth, that's the ecliptic. Okay? All right. Where what the sun would be ecliptic. Now, part A, the celestial pole and the equator. Okay? You see the picture at the bottom of the page. Yuck, I hit the wrong key. Okay? All that time I was thinking this was loading and it was something else loading. Okay, be just a minute. There we go. All right. What's that?
Oh, no, I was reading the portion.
Yeah. Okay. Now. Now.
The angle A and observable latitude is exactly the same as the angle alpha of north celestial pole.
Okay. All right. Now. I'm going to try to reproduce this because not everybody has books yet. But we're going to call this the Earth, right? Now the Earth is sitting here at a tilt, and I'll put that as the North Pole, okay? So this is the North Pole of the Earth, okay? Now this is the base of the celestial equator. I mean the celestial sphere, which we imagine. Now if the North Pole is here, that means the equator is here, right? Because it's 90 degrees from the North Pole, right? Now, if you draw the celestial sphere here, okay, this would be due north, this would be due south. That's your horizon. The North Celestial Pole would be somewhere here. And that would be the North Pole, North Star is what I meant to write, not pole. The North Star. But the better name for it, and this is what I was crossing up, North Star, actually the name is Polaris, meaning the pole star, okay? It would be somewhere here. Now, remember, all the other stars look like they spin around the North Star. The North Star never moves. It sits right there, and doesn't ever seem to move. All the other stars seem to move around it, okay? Even the stars down here, they go up and go down just as if they're going. Why? Because this is the axis of the Earth, and we're spinning around the axis. The stars are fixed in place. They're not moving. But we're moving, and it makes it look like they move. Okay? Have y'all ever been on a train and you pull into a station and another train looks like it's moving, and sometimes you can't tell if it's moving and you're still, or you're still and it's moving, or you're both moving. But it's just sort of a weird feeling. Find out, no, we're not really moving at all. He's moving. We're not. So that type of thing. Okay? Now, we live right here. Okay? In fact, here I am standing right here with no southern accent. Okay? Now, all right. Now, this is my celestial meridian, isn't it? From due north, directly overhead, to due south. Now, right at the top of me, there's a point that we give a sort of artificial name. Anyone remember what that's called? The zenith. Very good. The zenith. Okay?
What is the zenith?
It's just a point directly over your head. Directly over your head, on your local meridian.
That's all you have?
Okay. Now, because we are here in Bessemer, Alabama, okay, and I want to show you that I really know what I'm talking about.
I'm confused.
This is what I don't exactly.
Here is Alabama Gazette, a gazetteer or something like this, a atlas and gazetteer. It's a topographical map of the state. Here is Bessemer, Alabama, and if you read over here, we're sitting right near 33 degrees, 23 minutes, and 45 seconds. That's our latitude, how high we are above the equator. Okay? I'll get it in just a second.
So that's the equator,
That's
and we are.
Okay. Here's the equator, right here.
So that's
Right.
90 degrees.
There is, okay. There's 15 degrees, there's 30 degrees, and here's Birmingham at Bessemer, they don't show it on here, but it's 33 degrees, 23 minutes, 45 seconds north of the equator.
So wait.
Huh?
I was 23 minutes away.
What's the question?
Never mind.
Oh,
So
okay.
like 24
Okay.
minutes until the next degree.
All right.
After the-
So that's why I drew me there about a third of the way up. So that's our latitude. 33 degrees, 23 minutes,
Should we be
45 seconds.
on here?
What's that?
Should we be writing that on here?
You don't have to. I'm just sort of describing to you where this comes from. Now,
From zero,
what's that?
what's the minutes to time?
Okay. Minute is not minutes of time, it's minutes of arc. Okay? We're going to talk about that a little bit later too. Okay. All right. Let me give you a little bit of background. And this is just really sparse, and I'm not even sure it's all true, but I'm going to make it sound like it is. Okay. I think it was the Sumerians. Who? The ancient Babylonians. Before they were Babylonians, the culture that was there was called the Sumerians. They were one of the early civilizations. Remember studying about the Tigris-Euphrates Valley, the Fertile Crescent? They were the civilization, I think, that formed there. Okay? They started some of our number systems. And for some reason, they used something between a base 6 and a base 10 system. So, that's where we got 60 seconds in a minute, 60 minutes in an hour. Okay? And in a whole circle, how far is that? 360, which is 6 times 60, 360. Now, I don't know what their fascination with 6 was, but anyway, it was there. So a lot of things that we use, someone know? Okay. Yeah, are based on that, including arcs. 360 degrees makes a circle. That came from them. Where it came from, I'm not sure. Okay? And just like time is divided into, an hour is divided into minutes and seconds, so they divided a degree into minutes and seconds. 60 minutes makes 1 degree, 60 seconds make 1 minute of arc. Okay, so those are the minutes and seconds we're talking about. Degree, minutes, and seconds. We use single tick, double tick. Okay. Now, this is our zenith directly overhead, right? Now, if you did this 33, projected this 33 degrees, 23 minutes, and 45 seconds here, that would mean this would be our celestial equator. We are 33 degrees, 23 minutes, and 45 seconds north of the actual equator. So our zenith is 33 degrees, 23 minutes, 45 seconds north of the celestial equator. So that identifies where that is. Now, what they're asking here, here's the North Star. Okay? Now, they have identified this angle here they called alpha, because the commercial said, call alpha. No, never mind. Okay. Now, they named that angle alpha. Now, what they're suggesting here, what they're asking you to prove, is the angle that the North Star, it always stays in the same place. And the angle it is above your horizon, they're saying, prove that that is our latitude. Okay. Can we prove that?
Yeah, the North Star stays the same.
What's that?
I said the North Star stays the same, Rick.
North Star stays the same.
You got a record.
Okay?
All right.
So here's how you do it. And you do it however you see best. Okay? Started to write with my ionizing pen on my paper. It wouldn't write. Okay. This is that angle. Okay? This is our latitude. Right? Now this angle that's left over here above the south horizon, what would that be? What is the angle between our southern horizon and our zenith? Second? No, 180 would be this. Right, which is? 90 degrees. Okay? And remember, these two angles that had to be 90 are called complementary angles. That's C-L-O-P-L-E, right? Not P-L-I. So this would be they call it theta here, just to give it a name. But you know that theta plus our latitude must be 90 degrees, right? All right. Now, what's the angle between the celestial equator and the North Star?
180.
Right angle again.
Oh, yeah. So,
right.
So you just
Yeah.
basically turn the whole thing
Yeah.
90 degrees.
Yeah. If you went from North Star to South Pole, that would be 180.
Right.
The equator to North Star would be 90 again, right?
Right.
So this one we know this angle has to be a right angle, just as this angle has to be a right angle. Okay? Now, if this is 33, blah, 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 this is theta, these two had to be 90, but these two had to be 90, what would this one have to be?
90.
No?
45.
A little more than
Theta! This has to be 90, that has to be 90, so this one must be equal to that. Right? And if this one's equal to that one, and these had to be 90, guess what this has to be? 33, 23, 40. Yeah, that has to be alpha. We'll call it alpha.
Is this on the test?
What's that?
Is this on the test?
No, not this. But
Please tell me it's not.
Huh?
Please tell me it's not.
Goodness, this is easy stuff.
This is like the only part I don't understand.
This is geometry. This is math, man.
Yes.
This is fun. Is that what you said? Yeah. Okay. Math is fun. Okay.
Math is
And you want to dissect frogs? Huh? Okay, never mind. Okay. All right. No frogs today. Okay. So, That shows that this has to be, that our latitude is the same as that. And guess what? The sailors have used this time immemorial.
A compass.
No, this fact right here. When they're out in the middle of the ocean, how do you know where you are? Well, one thing that will tell you, at night, they have this thing called a sextant, and they find the North Star. How did they find it? What's the first thing they look for?
The brightest.
The Big Dipper. And the two stars at the end of that are called the pointer stars, okay? And they point to the North Star, so there's the North Star. And then they take their sextant and measure the angle. That tells them their latitude. Because the alpha, the distance the North Star is above the horizon, is the same as your latitude. Always, huh?
Your little Jesus fish.
That's the symbol alpha. In the Greek alphabet, alpha. Okay. And this is the Greek symbol theta. It's just what they named it.
Like a circle with a...
Yeah, with a horizontal through it. Yeah. Okay. I didn't think it would be that hard. Okay. So you see why that's true? Got it. All right. Now here's a fairly easy question, I hope. If the celestial pole makes an angle of 40 degrees over the northern horizon, at what angle above the southern horizon must the equator be? If this is equal to that, then these two add to be 90 and 40, okay. 40 plus what makes 90? 50. So this would be 50. This is the same as that, so that would be 50. Very good. If the celestial pole makes an angle 40 degrees above the southern horizon, at what angle above the southern horizon does the celestial equator make? That must be 50. Okay. Now, anyone know where Ecuador is? South America. Okay. Its capital is Quito. Quito. There it is, Ecuador. Guess what goes right through Ecuador? Equator. That's why they named it that. Ecuador equator. Right? And Quito sits almost smack dab on the equator. Okay? So, yes, here's what the question is. It says, second, suppose that you are at Quito, Ecuador, latitude 0. Where is your celestial equator?
In the middle.
On the right.
That's a very equator.
On the horizon? I would agree with that. If you're at the North Pole, then the equator would be on the horizon. But if you're sitting right on the equator,
It's at the top.
it's going directly overhead, east to west.
So the answer is over here.
Yeah, directly overhead, east to west. Directly overhead. Because your latitude, your zenith, see the celestial equator, if you were at Quito, Ecuador, turn the earth like this, the equator would be directly overhead, east to west. Celestial equator. And by the way, I hope you're already picking up on this. Anywhere that you see a question and some blank space, you need to put an answer. That's what I'm going to be grading. Okay? We can talk about all this, but if you don't write an answer down, yeah. Okay. Now, what's that? Number one was basically proving this thing we just did. So you write enough down to show that your latitude is the same as the angle, the altitude of the North Star. Okay. Now, Remember we said what the ecliptic was? That's the circle on the celestial sphere that this is where the sun travels, you might say. Okay? Now, I don't think we've hit it in the book yet, but it's on the lab there. That's what represents this too. Someone last time pointed out when I was asking about this, someone said it's tilted. How much is it tilted? 23.5 degrees. That is the tilt of the Earth relative to the rotation around the sun. In other words, the ecliptic, which maps the sun at any given time, is angled at 23.5 degrees from,
Thought that changed as we go around the sun. That how we get the different seasons. Thought that went back and forth.
Okay, the Earth doesn't go back and forth, we go around the sun. The Earth stays just like this. Now, when are we now? We are in August.
Yeah, between
Okay, so we're somewhere right about here. Okay, we're pointing to the North Star. Okay, we always point toward the North Star. Okay, and we're here. So we get quite a bit of sunlight. When September rolls around, the sun is directly over the equator here. So that's going to be our midpoint. When we move over here, the sun, you're the sun, by the way, you're really bright. Okay? All right. Over here, the sun is as far down as it will ever be. See, we stayed the same. We're moving around the sun. That's what makes the season. Then when we get springtime, we're back here, and you're right above the equator again. And then we go over there, and June the 21st, you're as high in the sky as you ever get. And it's all downhill from there. Okay. All right. So we don't move. We move around the sun, but we keep our tilt. We don't change our tilt. Okay. Where were we? Okay, here we are. And that's what this picture is showing. The ecliptic is a circle that is tipped at an angle, same as that angle, 23.5 degrees to the celestial equator. Okay? In this figure here, you see 47.2. It shows that. And this shows the, see, there's our North Pole. I'll do it like this. Our North Pole, South Pole. Okay? The celestial equator is halfway between those. And when the sun, and we go around the sun in a fairly regular, it's not a circle, it's an ellipse, but it's fairly, don't get ellipse confused with eclipse, it's slightly different. It is very different. Okay? And the summer solstice, the sun is as high above the celestial equator as it will ever be, 23.5 degrees. What, by the way, what does solstice mean? What does SOL mean? Sun! Okay, solar system, sol, sun. Okay? So the sun, okay, and here's what's happening. Every day in the summer, before June 21st, the sun goes up just a little bit higher above in its transit above our meridian, at our meridian. Every day gets a little higher until June 21st, it stops. Doesn't get any higher, and the next day it starts getting lower again. So when the sun stands still, solstice, sun is still. That's the maximum. Really, it came probably more from in the wintertime. In the wintertime, every day, the sun gets a little lower at the transit. A little bit lower every day until December 21st. And you see, the ancients, they always worried about that, because every day the sun didn't get quite as high. And the ancients feared that it would just keep falling, and then when it went down, you'd never have any more sun, and you'd freeze to death, because it kept getting colder and colder. And so every year, when it stood still and started going up again, they threw a party. The winter solstice. Okay? Now, this sounds almost like it's heretical, but I'm afraid it's true. What do we celebrate right around that? Christmas. And if you think about the shepherds watching their flocks at night, would they have been out in the middle of the coldest part of winter? Probably not. They would have had the sheep inside. But the Christians were being pretty clever about it. Early Christians, they were a minority, said, let's pick a time when they're partying anyway and give them something to party about, you know. So some people think that that's why they chose December 25th. Not because there's any record that's when Jesus was really born. Sorry about this. But that it was a party anyway. What's that? I'm sorry. I just messed it all up for you. Santa Claus isn't coming to you next year. All right. All right. So now there's 2 other days. Maximum height on summer solstice, it stands still then. It stands still again at winter solstice around December 21st. There's 1 day, though, in between when the sun, and by the way, in the summertime, the days are longer and the nights are shorter. And in the wintertime, the days are shorter and the nights are longer, right? Yes. Okay? What time of the year are they the same? Spring and fall. And what do we call those?
Daylight savings.
What?
Daylight savings.
Okay, we sort of do that based on it, but not exactly. What is the day when the daylight hours equal to the nighttime hours?
Daylight savings.
Second?
You're not talking about this daylight savings.
No, that we don't do that exactly. We do it wacko anyway, but yeah, that's not what we're going to talk about. It has a name for that. We call it the spring or fall equinox. And what does that stand for? Equal night is German for night. Equal night and day. Equinox. Okay? So, that's our equinox. And 12 and 12. Maximum daylight hours in summer, minimum in winter, equal fall and spring. On the equinox. Okay. And by the way, the spring one is sometimes called the vernal equinox. I don't know if that's Greek or what. I think for some reason I think green. Things get green then. But in the fall it's autumnal equinox. Okay? No question there's a lot of stuff. Okay? Now this shows you looking at the sunrise, sunset in the middle of summertime, and the middle of wintertime, and that's pretty much what this shows. So guess what? In summertime, when the sun's at the highest in the midday, it actually rises from due east, north of east, and goes up and goes down north of west. It's only on the equinox that it rises directly east, it doesn't go directly overhead, reaches and goes directly. So it's fall and vernal and autumnal equinox. The other times in the wintertime, it rises south of east and sets south of west. That's why it's such a short day. Okay? So that's what this picture is showing. All right. Now, as if we didn't have enough terms. Okay? We're talking about some object, say that star right there. Now, last time we talked about altitude, that's above our horizon. But we really need, our horizon changes wherever you happen to be, right? By a little bit. Yes? So, we need something a little more fixed. Why don't we talk about how high that is above our celestial equator, because that doesn't change, right? So then, the distance of an object above the celestial equator, that will be called the declination. Declination. That's a better thing for naming that, because it doesn't depend on where you are. That star is always the same place above the Earth's equator, celestial equator. Always. Okay? Now, there's another thing like azimuth that someone mentioned before, and they don't show it on this one. Okay? So declination is so far north of the celestial equator or so far south of the celestial equator. Here we go. The next figure on page 363 that shows what they call right ascension. Goodness, can you come up with enough terms here? So what are we going to measure the right ascension? Remember, that's the part that was really tough. When you're moving like this, the equator is fixed, and how far north to south, that's going to be declination. But how do you measure east and west? You have to pick some point. So why don't we pick the vernal equinox, where the celestial equator crosses the sun's ecliptic in the spring. That will be where we measure right and left from, and that will be called right ascension. Why right ascension? I have no idea. Okay? But that's what they call it. From the ecliptic, the vernal equinox to the right. So if we have how high the object is above the celestial equator and how far it is east or west from the vernal equinox, where the celestial equator crosses the ecliptic, that's one big point, then we can identify exactly where that star is. And that's what we're going to be doing. Now, how do we measure right ascension? Well, let's just pick something that measures left and right here. Okay? What are these numbers here that measure east and west? And we talked about this last time. There is one meridian that goes to the North Pole. All the meridians go to the North Pole, the South Pole. The one that goes through Greenwich, England, is called the prime, meaning primo, first meridian. Prime meridian, 0 degrees east or west. One that passes through Greenwich, England, Naval Observatory there. Okay? And then we measure them right and left from there. Now, what else do we measure right and left? Yes. Time. Zones, exactly. Okay? And that's why we measure right ascension in terms of hours and minutes. Strange but true. Okay? So we're talking about right ascension measured in hours. We call it an hour circle. Okay? Hours and minutes and seconds. But we also refer to the angle as hours, minutes, and seconds. Not hours, degrees, minutes, and seconds. Same thing y'all were asking about before. That's why I thought y'all were looking ahead. You must have figured that out. Okay? So here's the question.
So 60 degrees of arc would be equivalent to 1 hour right ascension.
Okay, say that one more time.
60 degrees of arc would be equivalent to 1 hour of right ascension.
Okay, I don't quite think so, but you're moving in the right direction. I'm going to take this one off and draw another one here. We're going to do, just because Ray is so fond of it, we're going to do a little more math, okay? Yes! Okay. Now, yeah, I can tell he's excited. Now, notice here on page 363, right above the paragraph just about in the middle, here is the peculiar aspect of right ascension coordinate. It's measured in hours, like I just said, subdivisions, minutes, and seconds of time, whereas degrees are also measured in minutes and seconds, but not of time, but of portions of an angle. So, they make a statement here, and here's what I'm going to ask you. How long does it take, say, the Earth to spin from this point back to that point again? 24 hours. How many degrees was that? 360 degrees. There we have a ratio, don't we? We love ratios, okay? So let's do our ratio. 360 degrees is equivalent to 24 hours, right? Now, the question is, how many degrees are equivalent to 1 hour of right ascension? That's called the proportion, isn't it? Two ratios equal to each other. Do you want to make this be a variable rather than a question mark? It doesn't matter to me. No, a variable. A, okay, why not A? Okay. All right. So how do we solve a proportion? Anyone know? It's really simple. Cross multiply. So this says that 24A is equal to 360. So what do we do for solve for A? Divide both sides by 24. Okay, this goes away. That leaves A is equal to, say again? 15. 15. Say again? No, you can do it any way you want to as long as the answer's right. Okay, all right. All I'm interested in is right answers, okay? So there's the answer to number 4. How many degrees of arc are equivalent to 1 hour of right ascension? We just solved it and found out it was 15 degrees. Which, by the way, what do you reckon the times on it? These are measured in 15 degrees. But what we're going to do is there's either side of it. So either side of this, you go up here, and that basically is central time zone right there. Right? That's how we get it. And then Eastern is 1 hour here, Mountain is 1 hour that side. Okay? 15 degrees, 1 hour. That's why we set our time zones. Okay? Now, next question, how many minutes of right ascension are equivalent to 1 degree of arc? Okay? How many minutes of right ascension? Okay, we need a ratio we know. Okay? And I think we just had this one, didn't we? We had that 15 degrees of arc is the same as 1 hour of right ascension. But we want minutes. How many minutes in an hour? 60. 60 minutes of right ascension. Okay? And the question asks, how many minutes of right ascension, there is our question mark now, is equal to 1 degree of arc. You want to put a variable in there, or are you happy with question marks? You want A again. He likes it. He likes A's. He wants A's all the time. You know, I know him. Huh? Will it be 15? Let's do the math. You want to use A again or something else? What you want to use? What is it?
I just checked it. I hope you don't mind.
Okay. 4, of course, because 15 will go into 60 4 times. So 1 will go into 4 times. So this will be 4 minutes of right ascension is equivalent to 1 degree of arc.
Oh, I was thinking a quarter.
Yes, okay, got it. All right. That's number 5. All right. How about number 6? How many minutes of arc are equivalent to 1 minute of right ascension? What's that? I couldn't hear what you said. Backwards?
Backwards to number 5.
Okay, and what do you mean by that?
Is it the same question?
No, it isn't. Not quite. Number 5 says how many minutes of right ascension are equivalent to 1 degree of arc. This is saying how many minutes of arc are equivalent to 1 minute of right ascension. Okay. What's that? Okay, I hear some mumbling, but I can't make it out.
Oh, no, we're just saying plug in the numbers.
Okay, well, let's go back to a ratio we know. There's a ratio we know. We just came up with it, right? Now, it says 1 degree of arc, but now we want minutes of arc. How many minutes in a degree? How many minutes in a degree? 60. Remember the Sumerians? Don't forget the Sumerians. They based, okay. So let's do 60 minutes. In fact, I'm going to use a little tick mark here of arc is equivalent to 4 minutes of right ascension. And then our question is, how many minutes of arc, there's our question mark now, are equivalent to 1 minute of right ascension. Okay? You may have said it right. I don't know. I heard the boom. 15, you got it again. 4 going to 60, 15. So 15 minutes of arc is equivalent to 1 minute of right ascension. All right, we got those 3. I feel like a dentist pulling teeth here. Okay.
Yeah, you're pulling teeth.
All right. Now we get to the fun part. It's all been fun, hasn't it? Okay. Ooh, I forgot to do something I meant to do. Let me do it quickly. When, I think I may have mentioned to you that my wife had professional meetings in Utah. Does anyone have a pair of scissors on them?
I have clippers.
Second?
I have clippers.
Clippers? Would they cut this string, you think? It's all right. I can do without it, but if not, I can use this one. That's fine. I got it untied. Oh, look at that. Look at that. He brings weapons to school. Lock him up. Okay. It was a trick. It was a trick. I think I can do it with less string than this. So I was going to cut this in 2. If I can get my fingers to work. Goodness gracious. How many physicists does it take to change a light bulb? Okay. Okay. Let's see if we can make that work. Let me throw it that far. Okay. I'm sorry. This shows I didn't plan ahead too much, did I? Now, I've never used this one. I just bought it. As I was going to say, my wife had professional meetings in Utah the week between summer and fall term. And most of the time, her meetings don't coincide with times that I can go with her. But this time, it fit almost exactly. I had to take one personal day off on that Monday so I could make the trip with her. And we had a great time. We got there early, not just for her meeting, but so we could do a little bit of traveling. And now we had gone to, we had gone to Yellowstone and Tetons a time or 2 before, and we just really enjoyed it. So we flew into Salt Lake, and we rented a car and drove up first to Idaho to Twin Falls, where Shoshone Falls are, which are called the Niagara of the West. Beautiful waterfalls, okay? Then we drove east until we got into Wyoming, and then went to Jackson Hole and the Tetons, and took 1-day trip up to Yellowstone. It was fantastic. And came back to Jackson for another day or so, and then went on to Salt Lake City for our meetings, and it was just a good trip. But guess what happened in the Tetons on Monday? Same thing that happened here on Monday. Except in the Tetons, it was total eclipse. So most of the stuff up there, I mean not most, a lot of the stuff up there was related to the eclipse. So they had these fantastic things. Now this is the one I got years and years ago from the planetarium at Sanford, at Birmingham Southern. The lady gave me several of these, and I've almost worn this one out. And there I found a nicer one there, and my wife bought it for me. Okay, so you get to use the new one that's never been used before. Okay, so what we're going to do, we don't have a celestial globe. So we can't turn that around, but we will use the night sky. This is called planisphere. That one called it the star and planet locator. Okay, so we're going to use this. Now I'll show you how to do the first one. Which stars are located at the following coordinates? And they give you first right ascension. Now the question is, where is right ascension measured from? Well, yeah. Okay, he's either teaching me or he's giving me the answer. Which is he doing? Okay. It's where the ecliptic crosses the celestial equator, but it crosses there twice a year. Which time are we talking about? The spring. In the spring. Okay. Now, on this, I know you probably can't see from where you're sitting, but you see this circle here is the celestial equator. It's listed as equator. Okay, celestial equator. This dotted circle here is listed as the ecliptic of the sun. So what we have to do is turn this until they cross, or jinxed one, okay? And there we have it right there. Now this string, what we hold is over that, and we hold it till the ecliptic crosses the celestial equator, right there. Can y'all see that? You probably can't. But remember that, in the spring, and that's going to be very close to March the 21st. Right on. Okay, now what we've got to do next is read right ascension. Right ascension is measured from that. And what is your right ascension here?
6 hours and 43 minutes.
Okay, 6 hours and 43 minutes. So now yeah, here we have it. You can't see it on all of this, but notice here is 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 6 hours and 43 minutes. 1, 2, 3, 4, 5, 6 hours and 43 minutes would be right about there. You have to do a little estimation there. Okay, 6 hours, 43 minutes. Again, it's estimate. Okay, now I need to pick out something there. There is a fairly bright star there. They don't give a name for it, but I'm going, okay, well, even better than that. We have a date here. This is sort of artificial. That says about July the 2nd. So what I'm going to do is turn July 2nd down here. Okay, until I get that over my hole. July the 2nd. All right. There's July 2nd. A little bit further, right about there. Now I was estimating, so I just want something close. So there is my right ascension. I moved it down there. Okay? Now, the reason I moved it down there, I have the biggest window here. I could have done up here, but some of that would have been behind there. I couldn't see it anyway. So I moved it down there. Now, what is the declination? What does declination measure? Degrees from what?
From that coordinate.
From what? I mean, from the celestial equator. And when it says minus, what does that indicate to you?
Negative.
Yeah, negative. What does that mean?
South.
South of the celestial equator. So we need to go somewhere south of the celestial equator. There's the celestial equator, and what does it say? 16 degrees. Okay, now we have to do some more estimation here. Okay, this is 90 degrees from the North Star. By the way, the North Star is at the center, and this is 90 degrees. So 16 degrees would be about a quarter of that, right? Because half would be 30, and another half of that would be 15. And look at there. Do you see a bright star somewhere there? No. Right there. Sirius. Are you serious? No. Now, how you spell that, Sirius? S-I-R-I-U-S. S-I-R-I-U-S. Sirius. Okay? So you can fill that in. Now. The what?
Does that mean feet inches? What does it mean? 39?
No, it's 39 minutes. Right ascension. Declination. You know, with an angle, it's degrees and minutes and seconds, and with time, with right ascension, it's hours, minutes, and seconds. Okay. Now, who wants to go next?
How we gonna do it?
Huh?
You're
going to do this. You're
I
going.
feel like I need to do it so I can figure it out.
All right. Good deal.
I don't know how though.
Okay.
You're gonna have to help me.
Okay. Where do we start? What did they list first?
This one?
Yeah, right ascension. And what's right ascension measured from?
6 hours.
The what?
No,
There you jinxing me again.
Yeah.
Okay. Where the celestial equator.
Okay,
Okay.
so what do I do?
Flip it over like that. So yeah.
Okay, so now.
Where the celestial equator crosses the ecliptic. Ecliptic is the dotted line here, and the celestial equator is this circle here. Okay, so you have to turn it until it crosses. But which ecliptic? Which times they cross? Spring. So turn until you got, March over there. See March is coming up? Turn.
Like, all the stars in that man.
Okay.
No, I can't
Look,
read.
look,
I
look.
can't read.
See, there's the ecliptic and there's the equator. There's where they cross, right there.
Right there.
And that's March 21st, right?
Oh!
Oh, you see it? Okay. Now you do right ascension, 6 hours and 22 minutes. Count this way. And every one of these little ticks here, that's 1, 2, 3, 4, 5, 6, and 22 would be about a third. That's a little over half. So a little less.
So
Yeah,
these
right about
numbers
that.
don't mean anything?
Yeah,
Oh, that's the
So
date.
pick that as June 25th. So
So I'm in this?
but turn June 25th down there.
And the declination.
Yeah, now we're doing declination. Once we get this lined up, we'll do declination.
We're doing.
June 25th, right?
South 50 degrees.
Okay. Now, what is your declination?
Negative 52 degrees.
52 degrees, 40 minutes south of the celestial equator? You're not going to see it on this, are you? No, you can't see it. No. All you get is, this is set up for from 40 to 50 degrees. That's where Jackson Hole the way was. The Tetons are 40 to 60. 40 to 50. 40 to 50. I wish I could have gotten one that was 30 to 40, but we couldn't find one there, so I'm going to order one. Okay? And guess what? If you see 40 degrees here, you can't see any further than 50 degrees there. So it's below the horizon. So what you need to do is pick out a constellation down there. You see the constellation? How about Lepus? L-E-P-U-S. Some star south of Lepus. L-E-P-U-S. We can't see it. It's not on this thing. If we had a celestial globe, we might be able to see it. I don't have one. But this is the next big thing. L-E-P-U-S. Some star south of Lepus. Something like that. Okay? Who wants to go next?
I was thinking that same.
Brave people.
Come on, people.
Alright, good deal. Okay, the Y chromosomes are getting, X chromosomes are getting way ahead of the Y's here.
All right, we're going to pick it up.
Okay. Where do you start?
Oh,
Where do we start?
US.
By the way, we can turn on both lights. Well, I don't know. Can y'all see the board again? Okay, he wants to go to sleep. Right? Alright. Where do you start? Okay, okay. Where we start is, where you had right ascension from? Yeah, where the equinox? Wait, not equinox. The equator crosses the ecliptic. Okay. And which one? Spring. Okay. So around March 21st. Put that down here. You see See? Okay, good. That's where you start. Now, how many hours do you count right ascension?
18.
30.
About 18 and a half.
Yeah.
Okay? So here are the hours here. 1, 2, 3, 4, 5, 6, 7, 8, 18 and about a half. So about halfway between that. That looks like around December 30th. No. Yeah. 29th and 30th. Yeah. So term that until December 30th. Okay. Now we want declination of what?
Plus 38.
Okay. So plus 38 means it's
North.
north of what?
Equator.
Equator. Okay, there's your equator right there. And 38 would be a little over a third of the way up. Because this is 90. So it'd be somewhere right in there. Do you see a bright star somewhere there? Oh, maybe right there. What's that?
Lyra.
Huh?
No, Vega.
Vega! V-E-G-A. Vega. Lyra is the constellation it's in. That would be Vega.
Which constellation? Lyra.
Yeah, but no, it says star name.
Lyra.
Yeah. No, the star is Vega.
Oh, Vega.
The
Vega.
constellation is Lyra.
Yeah.
Very lyrical name. Okay. All right. Who wants to go next? All right, everybody get a Y chromosome in the picture here. Okay. Can you read it polite? People are you sleeping? Okay. All right. Okay. Right ascension, 5 hours and 12 minutes.
Where's the
Where
right
do we start
ascension?
right ascension? Turn it around to the yeah. Where do we start? Where do you measure right ascension from? Okay, there you go.
For the equator.
Where the what? Equator crosses the?
Equinox.
No, eclipse. There's a lot of E words here.
Yeah.
Okay. And the equator is also right here. The ecliptic is the dotted circle. Oh, this is down here. So when does it cross? It's 2 times a year.
Spring, March 21st.
We want the spring.
Spring, March
The
21st.
turning of March 21st is down here. Where are you going along with?
Yeah, early spring.
What's that? Okay, you can just line it up on that thing right there. It's easier. Yeah, March 21st. Something like that. And you see there, it's right up. That's the ecliptic crossing the equator right there. Okay? And where do you count right ascension? It's 5 hours, 12 minutes. Oh no, don't move anything. Okay. This is 0. There's 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. 12 minutes is about a fifth of an hour. So that's a little bit, that's 5 hours, so it'd be a little bit past 5 hours. Okay, you can move it. Yeah, okay, yeah. Move the string if you want to. A little bit further. That's 5 hours. There, that looks good. Pick a date there.
June
7th or 8th?
Yeah.
Okay, flip, turn that around so it's down here, June 7th or 8th.
Turn this down here.
Yeah. That way you get the biggest viewing area. That's all right. Yeah, okay. Somewhere right about there. Okay, and what's your declination?
Negative 8 degrees.
15 seconds. Minutes. So there is a bright star, right? What is it? Rigel. R-I-G-E-L. Could be Rigel or Regal.
Riga.
Oh, you win again. Okay. Everybody get it? R-I-G-E-L.
You said A-L or E-L?
E-L, I think it's
Yeah.
E-L. Okay. Starting at March 21st. Deal. Share, you see the ecliptic crosses the equator. Okay, see? Here we go. Where do you go right ascension?
Right, so it'll be 7 hours.
And 37 minutes.
So,
These are 1, 2,
7 hours and what's that? 37 minutes.
37 minutes.
And we'll go about right there.
You know, about June
About
15th.
July 15th.
July 15th.
So let's go to July 15th.
Okay.
And we are
5 degrees, 21 minutes. And that's what does plus mean? North of the equator, so toward the North Star, so not very far above the celestial equator. You see the celestial equator? There's the celestial equator. Just above it. What's that? Yeah, Procyon. Good old Procyon. I've been missing Procyon. Let me spell it for you. Procyon. Procyon. Good deal. Next. Procyon. Procyon. Who wants next? All right.
Good job, man.
Okay. Where do you start? March 21st. Equinox. And that's where the equator crosses the ecliptic. There's the ecliptic dotted line and the equator is the circle. See, he messed it up. Yeah. All right. And then where do you count from there?
14 hours.
36 minutes. So you count clockwise for it. Wait. Out. 1, 2, 3, 4, 5, 6.
Oh, I'm in the wrong line. Welcome back. How many hours?
14. A little over half. Yeah. We got a date around October 20th. Turn that around for us at the top. I'll just have a look ahead to us, have we? Okay.
And then I go.
Yes, negative 60
South.
and 38.
Yeah, south. You can't see negative 60. That would be way down here somewhere. Nowhere close. So it's something south of Virgo. Something south of Virgo.
Why is it Virgo?
Well, that's just the constellation that's there. There's the name. You have to sort of turn it around with that. That's constellation Virgo. Something to the south of. South of Virgo, because you can't see it, it's not on. Yeah, south of Virgo.
Wait, that's what we need to.
Okay. Yeah, south of some star, bright star south of Virgo. VIRGO.
Let's go, man.
Okay.
That's it. That's what
Let's go to constellations now. There you go, easier because you just get close. Okay.
So how we do?
What constellation? Okay, who's next? All right, good deal.
Quick one, say I got.
Okay. All right. Where do we begin? Okay, where equator crosses what? Ecliptic. Okay. When is that?
In the spring.
In the spring.
March 21st.
March 23rd. I'll turn this around till March 23rd.
You were right.
This third March of birthday.
It's 21st.
I don't think this matters as much. It's like some projects for us to have to do together. I think.
See, this is
Yeah, you don't have
things
to
are
have.
going on. Sure about it. Maybe it's 7 Ah,
Thank you for making sure you go with some stuff.
you see that for the okay, and where do we count from there? 11 hours right ascension. So from here, keep that, don't do these things. So count 1, 2, 3, 11 hours around. 2, 4, there, yeah. This is the first one. No, okay, this is where that's 0, 1, 2, 3. See these little triangles there? Yeah. 1, 2, 3. 11. Yeah. That was what was it? September the 3rd. Doing that around to September 3rd. Something like that. Okay. And where do we go to declination?
Plus 50.
What does that mean?
North.
North. So here's the equator here. There's 90 north, so this is 50 north, so it's a little over halfway. What constellation do you see? A little over halfway between the equator and North Star.
Yeah, that's right. Yield back.
Okay? Either that or I think maybe the next up.
Ursa Major.
Ursa Major. What is Ursa Major, by the way? Major means big. Ursa is bear, the big bear. Now, what group of stars is in the big bear? The Big Dipper is in the big bear. So, Ursa Major. URSA MAJOR. If it's Ursula Major, let's know that's not right. Okay, Ursa Major. Okay. Next. Next. All right. Okay. Where do we begin?
Turn upside down.
Oh, everything's reasonable. Yeah, but by the way, oh, I didn't realize this. Yeah, I'm glad you pointed this out.
It's all on the back already.
Oh, you go past negatives on the back.
Let me see. It goes a little bit further, not much further.
Not the average.
Just a little bit. Okay. Let's use front. There's where we'll set up. Where do we begin?
March 21st.
March 21st. Which is? What's that?
Ascension.
Okay, yeah, that's where we start. But what is March 21st called? Eclipse, which is a dotted circle crosses the equator with the solar circle right there. Okay? Where do we go from there? They do it 19 hours? Okay, we'll go from there. Okay, 19 hours. So here's your hours. There's your 1, 2, 3, or you can jump right up to 12 here and go from there, or start at 18 here and go from there. I don't care.
First time you tag.
1 hour and take 1 hour back there. Right there. Okay. I spelled today.
One more line.
Huh?
One more line. Take one line.
Really? You're the 6th? Yeah. I'm the 7th. Really? Okay. Now, where do we go from there? Negative 25 degrees. I don't think that's going to show 25, so now flip it over. Now that you discovered that. And it may be this one. Aquila. Or something south of Aquila. 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 Or something south of that. Say again? Aquila. Yeah. He was the husband of Priscilla, right? Okay.
Mayor
I
Kentucky.
know.
No, that's not Greek. That's good.
Mayor Kentucky.
What's that?
Mayor Kentucky. I'll keep it Mayor Kentucky.
Oh. Okay. Who's next on that one? I think you know. Hunter raised the hand, didn't he?
Margaritas.
Thank you. I know. I have no idea how this is. Are you through already? Okay. Well, we're going to probably finish this next time, so don't put it in partial. Now, I'm supposed to, please tell me. Yes, I'm recording. But the thing is, I don't know if all this is being picked up because I'm all over the room. But I think Hunter was next. I should go back to the computer every time to spell these, but there was nobody absent, so I didn't bother with it. So I'll do it now. Where do you start?
March 21st.
Okay.
21st of March.
Okay, yeah, turn it so this is at the bottom. Sorry. All the way around. I don't know why they have it upside down. Now, what happens there? That's where the ecliptic, which is the light circle, crosses the equator, which is the solid circle, right there. Okay, and where do you go from there? Is it 3 hours this time?
Yep.
Okay, 3 hours. That's on my mind. So hours, count right. There's 1, 2, 3. Huh? Or you can rewrite. Right. That works just fine. That works fine. And then where do you go? Plus 20. So this is 0 to 90. So plus 20 would be somewhere in there. What would be a constellation? Yeah. Why not call it Perseus? Perseus.
Perseus.
Perseus. Who's next? Don't be shy. All right. Okay. Where do you start? March 21st. Yeah, okay. You there? No. Not in the
office. I'll type anything.
All right. Where do you start? Where do you go from there? 1 hour. Hour is little triangles right there. Yeah. So just bring out some business. Yeah, you can turn it and then you go where? Plus 60. This is the equator. There's plus 90 up here, so about 2/3 of the way up. You can turn it over. Okay. It's Cassiopeia. Cassiopeia. I'll have to spell it for you. Cassiopeia. I always thought it was Cassiopeia, but now I've been to the planetarium, it's Cassiopeia. Okay, I guess. Now that's the story of this another beautiful lady who got involved with some of the Greek gods and stuff like this, and or the goddesses or something. They got mad at her and chained her to a chair and she had to sit there in the chair and couldn't look at the mirror or something like that. I don't remember the story. So she's sitting in a chair. To me, that doesn't look at all like a chair. But it looks like a W. I thought it was a winner, but I can't figure this thing out. Okay, who's next? All right, good deal.
You're the next contestant on.
Okay. What are we on now? Plus 13?
Yeah, 2 plus 19 more questions.
Where do we begin? March 21st. Very good. And that is, by the way, you're on one side of it.
And then I'm checking Instagram.
There, close. What's true about that? Equator, which is a solid circle spring equinox. 13 hours. You count around here, these little triangles. Yeah.
Amphibian DNA.
13, okay. That's going to be after this. We'll send that around there.
I said one week.
Right there. Okay, now, the trouble is,
Oh, yeah.
too far down. Let's see if we show enough on this side. I don't think so. So there's the equator. So it's something south of Virgo. We don't know what. There's something south of Virgo. Some constellation south of Virgo. VIRG. Next.
All right. Next.
All right, last one. All right, good deal. Came through in the pinch. Okay.
What was that?
What was that?
Something south of Virgo.
Again?
Yeah, that was a constellation south of Virgo. March 21st.
Anyway, you do it every time. I'm just saying, I mean, history-wise, one was the first trouble.
Yeah, that's pretty close. It's where the ecliptic, which is the dash circle, crosses the equator, which is the solid circle. 1 week. 7 hours, okay. These are the hours, those little triangles. 1, 7. So that's what you like. Yeah, so we'll fit somewhere there. There. Okay. Yep. Okay. I think you mentioned right about there.
Like, where you get wings? Let's ask where you going.
The stars are the small constellations.
You don't get chicken from Walmart. You don't get from Walmart.
Because, you know, you need to go to YouTube. Yeah, go, yeah.
Where do you get that from?
Whole Foods or
I got
Target.
Publix.
Might actually be, might actually be Gemini.
Okay, they got the deals at Fourth Avenue, okay? I was just like, buy one, get 3 yours.
All right.
Well, come on with
It's hard to tell. 2 of them are close together. You can either put Canis Major, C-A-N-I-S, Major, M-A-J-R. Anyone know what Canis means? Huh? Dog, the big dog. Okay, he's the big dog in it. Okay, never mind. Okay. Okay. Or it could be Gemini. Anyone know what Gemini stands for? The twins, exactly. Minnesota. No, never mind. Okay. All right. All right. Now, flip to the next page. Relative amounts of daylight and darkness. All right. On the ecliptic, locate the position of the sun on June 21st. Anyone want to hazard a guess?
I'm going to say no.
He said he's not going to hazard a guess.
No. I'm just.
Oh, we're on page
Portion of 10. Right.
365, relative amounts of daylight and darkness.
Yes, portion
So
of 10.
on the ecliptic, locate the position of the sun on June 21st. Anyone want to hazard a guess where it is on June 21st? Huh?
No, it's in the west.
Highest point, okay. And where would that be relative to the celestial equator? North, very good. Huh? No, not that high north. The sun will be
North Star.
how far above the celestial equator?
93 degrees.
50, 23.
23
Yeah.
and a half. 23 and a half degrees. Okay? So here is,
Good job, X.
okay, now I'm going to show you how to do, I've got it on June 21st, and we're talking about the sun right there. Remember all the ecliptic, what is it eclipsing? It's eclipsing,
Negative 23.5.
okay, yeah, but it's positive, above the north. Okay, now, what I'm going to do is I find something close to that. Well, fortunately for me, they have put the this dash right there. That's where the sun is on the ecliptic. It's right a little bit east of that second little star off the Gemini. So that other one couldn't have been Gemini. There's Gemini's up there. So anyway, I'm going to turn that around until the sun's about ready to come up. See, I'm turning this, I'm turning this, I'm turning this, until that point that I'm looking for is just about to rise. There it is, somewhere like there. And let's see what time that would be.
Canis Major.
Oh, well, there it is. Sun's just about to rise there. And that looks like about 4:20 in the morning. Now that's a lot earlier than here. Why?
That's what?
Because this is 40 to 50 degrees north. We're at 33. But up there, the sun rises about 4:20 in the morning on June 21st. Have y'all ever traveled very far north?
No,
Canada. In the summer or winter or fall, spring, when?
Summer.
Summer. Did you notice how late the sun set and how early it came up? Yes, that's the reason. It comes up about 4:20. Okay? Now we're going to flip that around again. That same position. The sun is eclipsing that little spot right there. And I'm going to twist this around until the sun's right about to go down. Okay? Right about where it's going to set there. Looks to be about 7:40 in the morning. In the evening. 7:40 in the evening. 7:40 p.m. Okay? Oh, sorry. I wasn't answering the right question. The right question was, does the sun rise due east when it was over here? No, it rises north of east. Okay? I was looking at the wrong question. Does the sun rise exactly east on this day? No, it rises in the north of east. Now let me give you a little practical reason I know that's true. Our house tends to face basically due south. Okay? That means the back window, and I drive my wife crazy. I go around every morning and open the blinds. If the sun's going to come in, I open them so it reflects it up. If it's not going to come in, I'll open them just enough to get maximum light in, so I don't have to turn on lights. I'm really cheap. Okay, in the wintertime, however, I open the blinds so the maximum amount of sun comes in so it can heat the house passively. Drives very nice, okay? So, which makes it fun. Huh?
I do that too.
Oh, good. Good for
Especially
you.
at nap time.
Oh, no, yeah, no, that's
Because if the shades are down, then
Yeah.
the sun is shining on your floor and it illuminates the room. But
Oh.
if the shades are going up,
Yeah.
then it blocks the light.
Okay, she won't let me take it off. No, I'm just kidding. Okay. All right. So that's the answer there. Does the sun rise? And it's no. Now it says rotate the globe until the sun's okay. Rotate the globe until the sun sets, and I just did that. We're at the beginning of the horizon. The sun just disappears below the horizon. That's what I was doing on that. Okay? And it says, estimate to the nearest 15 minutes the amount of time the sun is above the horizon on June 21st. Now, if you were following, did y'all write down when I was saying the times?
4:20, 7:20, 7:40, 7:20.
Okay. Hike. Okay, never mind. Okay. He said it set at 7:40?
Yeah.
Okay. 7:40 p.m. Okay. And it rose at
4:20.
4:20 a.m. Okay. Now I can't subtract those because one's a.m. and one p.m. You know how to do subtraction of time? The p.m. you add 12 to it. So 7:40 would be the same as 1940, right? 1940. Y'all know military time? 1940. Okay. Now you can subtract them. Okay. It rose then. It set then. That's 15 hours and 20 minutes. So it says, enter your estimate on table 1. It said to the nearest 15 minutes. I did it to nearest 5 minutes. So that was 15 minutes and 20 seconds. So go over to the next page, page 366. Okay? Now they have a pretty serious error here. Notice that first column? They call it SEC of the sun. That makes no sense at all. What they mean is DEC, declination of the sun. And I told you that at the very beginning, and I asked you that. What is declination of the sun on June the 21st? Somebody answered.
420?
Say again?
420?
No, the declination. How far it was above the celestial equator.
33.
Say again?
23 and a half.
23 and a half degrees. So that would be the declination. Change that S to a D. And the declination of the sun is 23 degrees, 30 minutes. You can make it plus, you can put north, whichever you want to do. And what was the number of daylight hours?
15.
15 hours, 20 minutes. How do you get the number of darkness? Whatever's left. So you subtract that from 24, right? Except I don't want to subtract it from 24. Okay? Not quite, I don't think. No, you may be right. What's that?
So it'd be 840 out of 24 hours?
Yeah, out of 24. No, wait. Okay, 24 hours is really 23 hours and 60 minutes, right? Okay? And then subtract 15, you're right, 20 from that, and you get 8 hours and 40 minutes. So y'all were absolutely correct. Okay? But I want to show everybody how to do it. All right, December 21st. Anyone want to hazard a guess to the declination of the sun on December 21st? Say again? December 21st, declination of the sun. You can estimate it here. December 21st.
46.
Say again?
46.
47.
46, 60. Yes.
53.
Hi, no.
89.
Y'all sound like you're calling audibles. Okay. All right. I can't read this at all. I guess what this is showing is what you don't see here. Okay. But anyway, on December 21st, the sun is the lowest it'll be in the sky. Okay? Which is above or below the celestial equator? Below. How many below? 23 and a half below. So that would be
23.
Huh? Minus 23:30 or minus 23.5 or 23 minutes 30 seconds or minutes south, 23 degrees 20. Okay, whatever. Okay. Now.
So it's negative 23 and
It's negative 23 degrees.
23.5, however you want to say that. Okay, now what I have to do here, I'm having trouble picking out here. I have to pick out some star that the sun is going to eclipse at that time. And basically, it's going to eclipse that little piece of the right angle there. So I'm going to do that over and see what time the sun rises on that day. Okay? Sun rises then right about there. Okay? Turn this around here. Sun is coming just over the horizon right then, and that looks like about 5, 6, maybe 7:40 in the morning.
All right.
7:40 a.m.
All right.
And let's turn the sun around till it sets. Okay. Just before it falls below the horizon here. Right there. Pull this around here, and that looks about, okay, there we got it. There's 1, 2, 3, wait, I'm going the wrong way. PM, 7, 8, 9, maybe 9:20 p.m. Okay, so you call out to me what we just said? No, I got it wrong. Sorry about that. No. I went the wrong time. Where was it right? No, I had that wrong. Wait, here we go. That's, I counted from the wrong one. They have these things sort of backwards here. There's 12, 11, 10, 9, 8, 7, 6, 5, 4:20. 4:20.
It'll be another 1940 again.
Say again?
It'll be 1940.
No, 4:20. Yeah.
We're gonna do the.
Okay, 4:20.
That was 740.
Wait, 4:20. Is that what we said?
420.
Add 12 to it, and that's 1620 minus what time we said it came up? 740. Okay. Now we have to borrow 1 here, making that 15. But 1 hour is how many minutes? 60. So that would be 80 now. So now we subtract, and you get 40 minutes. And what's that? 8 hours. 8 hours and 40 minutes of daylight. That's on your thing. And then number of hours of darkness. So, say again? 1520, is that what you said? Everybody know how to get it? Okay, 1520 hours of darkness. Yes?
Okay, is this going December 21st?
Second, December 21st, yeah. Declination was 23, negative 23:30, negative 23.5, 23:30 south, or whatever you want to call, okay? Number of daylight hours, number of darkness hours. Okay, March 21st. Anyone else want to try this one?
Hours of darkness, 15 hours.
Say again?
Oh, I was saying about the hours of
Oh.
darkness. This would be the opposite.
Yeah, you subtract it from 24, or 2360. Okay? Anyone want to try the March 21st? Someone who didn't do one before. Someone didn't do one before. Hey, we didn't do one before.
Give it here, man. Give it here.
Come on.
Oh, you got it.
That's what I'm talking about.
Okay.
Thank you, man.
Okay. Take it with. You're filling out the other one. Oh no, you're filling out the other one. Okay. March 21st. Where is the sun on March 21st? First, what's its declination?
March 21st.
What's that? It's the eclipse, which is the dotted circle. And where's the equator? The equator is the solid circle. And where is the eclipse? On March 21st?
Yeah, March.
They cross. So where is the sun? Right on it. So what would be its declination?
23.
It's right on it.
Oh, 0.
0.
And you guys, Sam. Come on, Kill.
Now, so it's really easy to pick out. So the sun's right there. So turn it over to the morning hour. And so that just comes up. Just coming over the horizon. Right there. Guess what time that is? 6 a.m. Okay? And you turn it around till it sets. Where the eclipse crosses the celestial equator. You want to hazard a guess? Say again? It's 6 p.m.
6
So we got how many hours?
12.
12 and 12. Guess what day we call that? Equinox. Equal day, equal night. 12 and 12. All right. Say again?
Is it 6 o'clock for daylight, 6 o'clock for
6 a.m.
Yeah.
Sunrise.
12 hours. 12 hours.
12 hours. 12 and 12. Equal day, equal night, equal night. Okay. All right.
All right, don't knock it out for today.
We don't want to start another section.
All right. Have y'all all brought your heavy coats? We're going up to Altegard, Norway.
All right, they do.
Latitude 70 degrees north. Okay?
Norway. Yeah, 47.2.
Okay, this is on page 366. I can't see where this is on the page 365. Oh, there it is. It says repeat this from December 21st to March 21st and readjust positions. We don't have this, so we're going to have to do this on our own. Altegard, Norway. Okay? What is the declination of the sun on June the 21st in Altegard, Norway? Say again?
He said the sun will go there. It's too cold.
Where is the sun on June the 21st? 23 and a half degrees north. That's its declination everywhere on June 21st. Okay? Now, and by the way, 70 degrees north, Altegard, Norway, that's way up there. Guess what that's north of?
It doesn't get any more north.
Huh?
what is it called?
Way up there. Altegard, Norway. Okay, the sun left, I guess. So it's darkness again. Okay, I guess Rachel will have to be the sun now. Here's Altegard, Norway. They don't really show it, but 70 degrees north is somewhere right up there. By the way, 70 degrees north is north of the
Equator.
Yeah, it sure is north of the by a long shot. Okay. What else is it north of? The Arctic Circle. Okay, and inside the Arctic Circle, on June 21st, okay, you're the sun, and this is June 21st, so facing right towards you. Tell me when you see Alsgaard, Norway, right up here, disappear.
Now.
Actually, I don't have to turn right. If I was down here, you still see it. North of the Arctic Circle, on June 21st, the sun never sets.
Get out of here.
So we just.
I do not. Okay, notice the days are getting longer the further you go north. North of the Arctic Circle, the sun never sets. 24 hours a day. Yeah.
24 hours a day.
And how much darkness?
None.
0. How about December 21st?
Same.
Yeah.
Same?
No, the opposite.
Meaning?
So it'd be 0 hours.
0 hours a day.
0 hours of daylight and 24 hours of darkness. Well, we did the declination of the sun on December 21st. What's that? Negative 23 and a half, of course. Everywhere it's that. That's the declination of the sun. Okay, on Arctic Norway in springtime, March 21st. What you reckon what's the declination of the sun now? 0. And what would be the number of daylight hours? 12. Number of, equinox, right? Equal day, equal night, everywhere on the planet. All right. Okay, let's go to Keto Equinox. Yes. Sorry.
You call
I'm taking your answer.
You got it right. You got it right. And then
I
the
done
next
this
one
whole
was 6.
I just get this top.
Okay.
Don't ask me what this last.
It doesn't matter what you say. Anyway, the sun is the same declination on March 21st, all around the world, July 21st, June 21st. The declination doesn't change. Once you figure it once, it's good for all of that day. Okay. Now, what's your question?
Yeah, you throw all of
Set
it.
it all away. What?
What for the third one?
Yeah. How about December 21st?
Well, yeah.
Okay, now, December 21st. The Arctic Circle, north of the Arctic Circle. Okay, you tell me, here's Altegard, Norway. You see it? No, you don't. It's north of the Arctic Circle. Never gets 0 hours of daylight, 24 hours. Okay? How about March 21st? Was it the declination of the sun? Okay, the hours of daylight and darkness 12 and 12. What's the declination of the sun?
0.
0, exactly, because it's on the equator. The sun is right there on the equator, 0 degrees. All right, now we're going to Quito, Ecuador.
Let's go.
Okay. Pull out the lights.
What's the weather like?
Huh?
What's the weather like? Get ready to cook?
Actually, Quito, being right on the equator, you would expect it to be quite hot and muggy. But it's at a high elevation, so it's very pleasant year round. Okay, warm. Okay. Okay, Quito, Ecuador. What is the declination of the sun? 23 and a half degrees.
Yes, sir.
Positive on June 21st.
Yes.
How many hours of daylight and darkness at Quito, Ecuador?
0.
It's dark every day.
It's on the equator.
0. Equal.
Equator, they're equal. 12 and 12, 12 and 12, 12 and 12.
12 isn't we equal?
Yeah. I actually equator means equal, exactly.
That's right.
We had a student in this class several years ago now who was from Kenya, I think probably near Nairobi, but may not have been in Nairobi. But Kenya, again, is sitting right on the equator. She said the hardest thing she got used to when she came up here to go to school, she said, the number of daylight hours changed. She had lived all the time near the equator. She thought all days were 12 hours of sunlight and 12 hours of darkness. On the equator, they are year-round. Equator, equal day, equal night.
So,
What's that?
I would like that,
I think I would too.
That's a real day.
I had a friend in high school whose sister was married to a guy in the Army or Air Force, I think. He was stationed in Hawaii, and that's near the equator, not right on it, but it just about all the time is the same, all year round. And she hated it because, oh, it's always the same. I thought, give it to me. Okay, that kind of pleasant weather. My nephew was stationed in Hawaii in the Navy, and he said, another day in paradise. Every day I get up, another day in paradise. He loved it there. Okay, so we've answered those three. Now we got to go back one page and get number 11 and 12. We didn't get those done.
What about December 21st and
What's that?
March 21st for that last one? Did we do those?
12,
Is that all the same?
Yeah. Now the declination of the sun is the same as it was at every place else.
Yeah.
Plus 23.5, minus 23.5, and 0. Okay? And on the equator, 12, 12, 12, 12, 12, 12, 12, 12, 12. Okay. Now, number 11 back on page 365, calculate the altitude of the sun in degrees over the southern horizon at noon on June the 21st for an observer at latitude 40 degrees north. Okay? Back to the drawing board, folks. All right. What we have to do here is draw a little globe. I don't draw globes well. Okay? Here is the North Pole. Okay? So the celestial... Oh, wait, I shouldn't do that yet. Okay. I need to draw the person first. I don't think it's going to make a lot of difference, but let's do it first. Okay. All right. Here's your horizon. And here's the celestial sphere. Okay. And here you are standing here. And you're at 40 degrees north. Okay, 40 degrees north would be about like that. So here's your equator. There is your zenith. And 40 degrees would be about like this, I'm guessing. I don't draw these things too well, okay? So this is 40 degrees north, okay? All right. So this is the celestial equator. Okay, you tell me. Okay, that's our picture. 40 degrees north here, 40 degrees north there. Okay? Now you tell me, and there's, by the way, this is northern horizon because the North Pole is here. So the North Star is something like that. May not be right. Polaris or North Star. Okay. I probably don't have it quite right. Okay. Calculate the altitude of the sun in degrees over the southern horizon at noon on June 21st for an observer at latitude 40 degrees north. Okay? Now, what do we need to know before we can figure that? I heard mumble, mumble. Okay. Okay, what we need to know is where the what the declination of the sun is on June 21st. And what is it?
Positive.
23.5 degrees. So 23.5 degrees is going to be a little more than half that. So here is the declination of the sun, 23 degrees, 30 minutes. North of the celestial equator, right? So there's the sun, shining brightly, okay? So what we need to know is how far above the southern horizon, here's the southern horizon here, what is the altitude of the sun at noon on June 21st when you're at 40 degrees? Say again? Well, first, what angle is this? 50. There's 50 degrees. You know, those have to add to 90. And then you're 23.5 past that, so it's 73 degrees, 30 minutes. Very good. Does everybody see that?
Yes, sir.
Okay.
30.
What's that? Everybody got it?
Wouldn't it just be the same with negative
What's that?
for December 21st?
Okay, what about December 21st? What's negative?
Wouldn't it just be 7330? The negative?
Yeah, the 2330 will be negative, so that will be here. So this is 21 June. This will be 21 December. Here's the sun, shining not quite as brightly, okay? And this is 23:30 south of the celestial 30 minutes, okay? So, what will be the altitude of the sun on that day? Say again?
Is it like, it's like 80 something?
That's 50. You come back 23. So, say again?
27 degrees.
27?
No.
26.
It's 26.
It's a little more than 23, so it'll be a little less than 27. 26:30. 26 degrees, 30 minutes. If you want to see how to get that, you do. Okay, let me show you. You start at 50 degrees, except I don't want 50. I want 49 degrees, 60 minutes. Isn't that 50 degrees? And then subtract from that 23 degrees, 30 minutes. And that gives you 26 degrees, 30 minutes. Okay, 26:30. And our little alarm clock went off. Okay. So, next time, when we come back, and we can either do it the first of the time or during lab time or whatever, let's do it right at the first, okay? We'll answer 13, 14, 15, 16, and 17. We came that close, missed it by that much, okay? Yeah. So, first thing we'll do is finish the lab, then we'll continue in chapter 15, then we...
I have a
Yes.
question. If I only took pictures of notes and such,
Yeah.
so I don't have them all written down, can I use my phone on the test or no? No, just the paper. It's
Yeah.
okay.
Yeah, just a piece of paper.
Okay.
You can copy it off your phone, can't you?
Okay, yes.
Yeah.
You can use the PowerPoints that you have out there.
What's that? If you wanted to print off the PowerPoint, it's not on there yet, but if I can get it on there before Tuesday, I'm going to try.
That's what I asked him.
All right, good class, folks. Y'all are a good group.